Look up at the night sky on a clear evening, and you'll see a familiar tapestry of stars, pinpricks of light that have guided explorers, inspired dreamers, and shaped our understanding of the cosmos for millennia. We've grown accustomed to thinking of galaxies as predictable structures, spinning in graceful accordance with the laws of physics, bound together by dark matter and shaped by gravity over billions of years. But what if I told you that some galaxies out there don't just bend the rules, they shatter them? Imagine gazing into the depths of space and discovering a galaxy so strange, so utterly unexpected, that it calls into question everything we thought we knew about how the universe works. These aren't science fiction, they're real, they exist, and they're rewriting the cosmic rulebook right before our eyes. These enigmatic galaxies are more than just cosmic oddities. They are profound mysteries that challenge the very foundations of astrophysics. From vast, ghostly structures almost invisible to our telescopes, to perfectly symmetrical rings that seem too elegant to be formed by violent collisions, each one tells a story we're only beginning to decipher. They defy prediction, resist explanation, and push the boundaries of what we believe is possible. In doing so, they invite us to question not just how galaxies form, but how matter, energy, and even time itself behave on scales we're only starting to comprehend. They are, in every sense, physics-breaking anomalies, structures that shouldn't exist, yet they do, shining a light on the gaps in our knowledge and the thrilling possibilities waiting just beyond. In this video, we're setting out on a journey to explore these cosmic rebels, from ultra-diffuse galaxies that drift like phantoms through the void, to dark matter-deficient systems that stand as monuments to the unknown. We'll uncover why these formations baffle the brightest scientific minds, what they reveal about the hidden workings of the universe, and how each discovery doesn't just provide answers, it opens up new, deeper questions. This is more than a tour of strange sights. It's an invitation to look closer, think bigger, and rediscover the awe that comes from confronting the magnificent unknown. So join me as we step into the shadows of deep space, where the rules are broken, expectations are overturned, and every observation brings us closer to the next great revelation. For centuries, astronomers have pieced together a cosmic rulebook, a beautifully coherent story of how galaxies come to be. It all starts with the faintest whisper of gravity, acting on the nearly smooth distribution of matter and energy in the infant universe. Imagine the cosmos just after the Big Bang, a vast, hot soup of particles. Tiny quantum fluctuations, ripples from the universe's very birth, create slightly denser regions. These regions act as seeds, and over hundreds of millions of years, the irresistible pull of gravity, amplified tremendously by the presence of mysterious, invisible dark matter, causes these seeds to grow. Vast halos of this dark matter form first, creating gravitational wells so deep that ordinary atoms, hydrogen and helium gas, have no choice but to flow into them. This is the foundation of our standard model, known as lambda cold dark matter, or lambda CDM, and it provides the stage for all that follows. As this primordial gas falls into the dark matter wells, it doesn't just sit there quietly. It collapses, it spins, and it begins to heat up through countless collisions. But then, something crucial happens. The gas must cool. It radiates away its energy, allowing it to condense further into dense clouds. Once these clouds reach a critical density, the first stars ignite in a brilliant flash of nuclear fusion, lighting up the darkness. These are not the gentle stars we see today. These first stars are behemoths, giants that live fast, die young, and in their spectacular supernova deaths, they seed the surrounding gas with the first heavy elements, the carbon, oxygen, and iron that will eventually form planets and life. Gravity continues its work, pulling these early stars together into the first proto-galaxies, and over billions of years, the story is written through a cycle of mergers and steady growth. We see the results of this process all around us, categorized into a familiar cosmic zoo. There are the majestic spiral galaxies, like our own Milky Way and our neighbor Andromeda. These are characterized by their flat, rotating disks of stars, gas, and dust, where new stars are constantly being born in graceful spiral arms, all orbiting a central bulge. Then there are the elliptical galaxies, massive balls or eggs of older, redder stars, which show little rotation and almost no active star formation. These are thought to be the products of major galactic mergers, where spirals collide and their structures are violently scrambled into a new, smoother form. And finally, there are the irregular galaxies, the misfits without a defined shape, often smaller and thought to be the building blocks that merge to form the larger structures we see today. This entire narrative is elegant, powerful, and backed by sophisticated computer simulations that can, in principle, recreate the universe we observe from its earliest beginnings to the present day. It gives us a baseline, a prediction for what a galaxy should look like based on its mass, its environment, and its age. But this rulebook, for all its success, is not complete. The universe, it turns out, is far more inventive than our theories, and the most fascinating discoveries are the ones that don't just follow the rules, but tear them to pieces. Now, let's turn our attention to one of the most haunting and counterintuitive discoveries in modern astronomy, the ultra-diffuse galaxy. Imagine finding a cosmic structure that spans the same immense volume as our own Milky Way, a staggering 100,000 light-years from end to end. You would naturally expect it to be a brilliant beacon teeming with hundreds of billions of stars, but instead, this galaxy is a phantom. It holds a mere 1% of the stars our galaxy does, its stellar population so sparse, so desperately thin, that it is almost completely transparent. If you were to fly through it in a spaceship, you might not even realize you were inside a galaxy at all. The stars are so few and far between that the surrounding void of intergalactic space would feel just as empty. These are the ghosts of the cosmic void, and their existence is a profound puzzle that strikes at the heart of our understanding of dark matter and star formation. The discovery of these galaxies was, in itself, a triumph of technological ingenuity. For decades, they simply slipped past our surveys, their light so faint and spread out that they blended seamlessly into the background glow of the night sky. It took specialized, incredibly sensitive telescopes like the Dragonfly telephoto array, literally a suite of repurposed camera lenses designed to detect the faintest of glows, to finally pull them into focus. One of the most famous examples is Dragonfly 44, located in the Coma cluster. When astronomers measured its mass, they received their first major shock. By observing how fast its few stars were moving, they could calculate the gravitational force holding the galaxy together. The stars were orbiting far too quickly for the amount of visible matter present. The only explanation was that Dragonfly 44, despite its ghostly appearance, was embedded within an enormous, massive halo of dark matter, weighing as much as our own Milky Way's halo. This was the first rule broken. Standard models predicted that a galaxy so faint and diffuse should have very little dark matter. It should have been easily torn apart by the gravitational forces of its neighbors in the dense cluster. Yet there it was, not only surviving but thriving, its stars moving serenely under the influence of this immense, unseen anchor. This resilience is what truly baffles experts like astronomer Pieter van Dokkum. He has described these galaxies as failed galaxies, but that term might be too simple. In the violent environment of a galaxy cluster, the gravitational tides from larger, passing galaxies act like cosmic shredders, pulling apart objects that aren't gravitationally robust. A galaxy as faint as Dragonfly 44, if it were just a collection of stars with little dark matter, should have been ripped to pieces billions of years ago. The fact that it hasn't been means its dark matter halo is not just present, but it's configured in a way that makes it exceptionally durable. This suggests that the relationship between visible matter, dark matter, and the process of star formation is far more complex and varied than our models account for. Perhaps some mechanism prevented gas from collapsing to form stars in these dark matter halos, leaving them as vast, star-poor relics. Or maybe they are the ancient, stripped-down corpses of once normal galaxies, though even that explanation struggles to account for their sheer number and peculiar stability. The mystery of their formation is as deep as the voids they inhabit. Did they form this way as primordial and quiet failures, their gas never igniting into a full storm of starbirth? Or are they the survivors of a cosmic catastrophe, galaxies that had their stellar gas stolen by ruthless neighbors, leaving behind only their dark matter skeletons and a few lingering stars? Each ultra-diffuse galaxy we find is a silent challenge to our theories, a whisper from the dark that tells us we are missing a crucial chapter in the story of galactic evolution. They force us to ask not just how galaxies form, but how they can fail to form in the ways we expect, and what invisible architectures allow these fragile-seeming structures to persist for billions of years. This ethereal mystery is just the beginning, a gateway that leads us to even more bizarre and impossible structures waiting in the darkness. But if ultra-diffuse galaxies are the cosmic ghosts, then ring galaxies are the universe's most stunningly perfect works of art. Picture a celestial bullseye floating in the blackness of space, a brilliant, luminous ring of blue young stars and active stellar nurseries, encircling a central, older, golden core of stars. It's a structure of such breathtaking symmetry and geometric perfection that it feels almost designed, a cosmic dartboard that defies the chaotic, violent processes we usually associate with galactic evolution. For a long time, the accepted explanation for these rare formations was a dramatic and destructive one, a head-on collision. The classic example is the Cartwheel Galaxy. The theory goes that a smaller galaxy, like a bullet, shot straight through the center of a larger spiral disk galaxy. The gravitational shockwave from this incredible impact sent a titanic ripple of dense gas and dust rushing outward through the larger galaxy's disk. As this wave expanded at thousands of kilometers per second, it triggered a frenzied burst of new star formation at its leading edge, creating that spectacular, glowing ring of young, hot stars we see today. The central core, left relatively undisturbed by the collision, simply settled back down, leaving us with the iconic ring and core structure. It's a fantastic story, a cosmic fender bender of epic proportions that seems to neatly explain what we see. However, the universe, in its infinite complexity, throws a wrench into this elegant theory, because not all ring galaxies show any evidence of such a violent past. Take Hoag's object discovered by astronomer Art Hoag in 1950. Here is a near-perfect ring galaxy, but it sits in profound isolation. There is no culprit galaxy visible, no trail of debris, no sign of a recent gravitational struggle. The ring itself is almost perfectly circular and symmetrical, with a clear, vast gap of dark space separating it from the central core. A collision severe enough to create such a pristine ring would have left the entire system reeling, with distortions, tidal tails, and other signs of recent trauma. Hoag's object shows none of that. It appears serene, stable, and utterly alone. This presents a monumental puzzle for astronomers. The statistical likelihood of a direct bullseye collision is incredibly low to begin with. For such an event to then produce a ring of such perfect symmetry, and for the perpetrator to have then vanished without a trace, stretches credibility to its breaking point. It forces us to ask a radical question. Could such perfection be born from a process of quiet, internal cosmic choreography, rather than a violent external crash? Researchers grappling with this mystery have proposed several alternative, gentler theories. Perhaps it was a process of resonant density waves, a subtle, rhythmic gravitational interaction within the galaxy's own disk that organized the gas into a coherent ring, much like the spiral arms in our own Milky Way are thought to form, but taken to an extreme. Another compelling idea involves a phenomenon known as a secular evolution, a slow and steady redistribution of a galaxy's mass over billions of years through internal instabilities. In this scenario, a central bar of stars could form and then slowly dissolve, funneling gas outward to a specific resonance radius where it piles up and forms new stars in a ring. There are even more exotic proposals, such as the accretion of a vast cloud of intergalactic gas that was ripped apart by the galaxy's gravity, settling into a ring. Each of these theories attempts to explain the elegance without the violence, but none yet provide a complete and universally accepted answer. The existence of Hoag's object and other isolated ring galaxies stands as a beautiful contradiction. They are structures that appear too perfect for a messy universe, suggesting that the forces shaping galaxies can operate with a subtlety and an artistry we are only beginning to appreciate. Just when we thought we had a handle on the strange and ethereal nature of ultra-diffuse galaxies, the universe presented us with an anomaly so shocking it seemed to pull the very rug out from under modern cosmology. For decades, one principle has been considered as fundamental to our understanding of the cosmos as gravity itself. That dark matter is the invisible scaffolding of every galaxy. This mysterious substance, which does not emit, absorb, or reflect light, is believed to make up over 80% of all matter in the universe. It's the gravitational glue that holds galaxies together, the essential ingredient that allows them to form in the first place and prevents them from flying apart as they spin. Every galaxy we've ever studied, from the mightiest ellipticals to the smallest dwarfs, has shown the unmistakable gravitational signature of being dominated by this unseen mass. It is the cornerstone of the Lambda-CDM model, the very foundation upon which our entire cosmic rulebook is built. So, what happens when we find a galaxy that appears to break this most sacred rule? Enter NGC 1052 DF2, a galaxy that sent shockwaves through the astronomical community upon its detailed study in 2018. DF2 is what's known as an ultra-diffuse galaxy, similar to Dragonfly 44, but with one Earth-shattering difference. When a team led by astronomer Pieter van Dokkum measured the velocities of its star clusters, 10 faint, fuzzy balls of stars orbiting the galaxy's main body, they expected to see them whizzing around at high speed, held in place by the powerful grip of a massive dark matter halo. Instead, they found something that seemed almost impossible. The clusters were moving slowly, almost lazily. Their speeds were so low that when the researchers calculated the total mass required to keep them bound to the galaxy, it matched almost exactly the mass of the stars and gas they could see. There was no room left for dark matter. In a universe where dark matter is supposed to be the dominant player, NGC 1052 DF2 appeared to be made of nothing but the ordinary, visible stuff. It was like finding a towering skyscraper that somehow defied gravity, yet upon inspection, you discovered it was built without any steel framework. just the glass and drywall standing tall against all expectations. The immediate reaction, as with any finding that challenges a core paradigm, was intense skepticism. Could this be a simple error in measurement? Perhaps the galaxy is oriented in such a way that we're not seeing the true motion of the clusters. Or maybe it's much closer or farther away than we think, throwing off all the calculations. The team, including researchers like Shani Daniley, have tirelessly worked to rule out these alternatives. Follow-up observations with the Keck Observatory and the Hubble Space Telescope have only reinforced the initial conclusion. They even found a second galaxy in the same category, NGC 1052 DF4, which shows the same startling lack of dark matter. This made it harder to dismiss as a one-off fluke. The evidence is mounting that these galaxies are real, and their existence forces us into a corner where we must ask profoundly difficult questions. Did these galaxies somehow form without dark matter to begin with, or did they have it and then have it brutally ripped away? This is where the mystery deepens from a simple oddity into a fascinating cosmic detective story. Both of these dark matter-deficient galaxies are located near a massive elliptical galaxy called NGC 1052. One compelling theory suggests that they were once normal dwarf galaxies, each with its own dark matter halo that ventured too close to this giant. In a process called tidal stripping, the immense gravitational tide from NGC 1052 could have torn away their dark matter while leaving the more tightly packed stars relatively unscathed. It's a galactic version of a theft where the thief only steals the invisible scaffolding, leaving the visible building oddly intact. However, this explanation is not without its own problems. The simulations of such interactions are messy and often leave clear tidal debris streams of stars stretching out into space, which we don't strongly see around DF2 and DF4. Furthermore, the star clusters in DF2 are old and calm, showing no signs of the violent disruption such a traumatic event would likely cause. This leaves open the door for even more radical possibilities. Could our understanding of gravity itself be incomplete on galactic scales? This is the territory of theories like modified Newtonian dynamics, or MUND, which proposes that what we attribute to dark matter is actually a modification of the laws of gravity at very low accelerations. While MUND has had some success explaining certain galactic rotation curves, it struggles with the specific case of DF2. Its predictions don't neatly align with the observed motions there either. Alternatively, perhaps dark matter is even more bizarre than we thought, possessing properties that allow it to interact with itself or with normal matter in ways we haven't yet dreamed of, creating scenarios where it can be separated from the stars it is supposed to anchor. The existence of these seemingly impossible galaxies is not a death knell for dark matter. Instead, it is a powerful catalyst. It pushes our models to be more nuanced, more creative. It tells us that galaxy formation is not a single monolithic process, but a diverse set of pathways with different outcomes. The discovery of NGC 1052 DF2 and its kin is a brilliant reminder that the universe is under no obligation to conform to our textbooks. It dares to create structures that defy our most basic assumptions, and in doing so, it guides us toward a deeper, more complete truth. The absence of the invisible in these galaxies is perhaps one of the most significant clues we have, pointing toward unforeseen and thrilling new chapters in the story of cosmic evolution. If the discovery of dark matter-deficient galaxies felt like a cosmic theft, then the next anomaly is more like finding a hidden giant living in a tiny cottage. We've long understood that there's a fundamental relationship, a kind of cosmic harmony between a galaxy and the supermassive black hole at its heart. In large galaxies like our own Milky Way, the central black hole, while still monstrously heavy at millions of times the mass of our Sun, represents only a tiny fraction of the galaxy's total mass. It's a proportional relationship that holds up across the universe. Bigger galaxy bulges host bigger black holes. This scaling law is a cornerstone of our models, suggesting that galaxies and their central black holes grow together, co-evolving over billions of years through mergers and regulated by feedback. But what happens when we peek into the smallest, most unassuming galactic neighborhoods and find a behemoth that shatters this delicate balance? Welcome to the bizarre world of dwarf galaxies with overmassive black holes. A dwarf galaxy is exactly what it sounds like, a small, faint, and often irregular collection of a few billion stars, a mere speck compared to the grand spirals and ellipticals. These are the cosmic backwaters, the quiet villages of the universe. Yet, astronomers peering into these villages are increasingly finding something astonishing: central black holes of staggering size, utterly disproportionate to their modest surroundings. It's the equivalent of a small, quiet town having a power plant the size of one designed for a continent-spanning megacity. The most famous and compelling example is a starburst dwarf galaxy called Henize 210, located about 30 million light-years away. For years, it was a subject of intense debate. Some astronomers argued the bright, compact radio source at its core was simply a remnant of a powerful supernova. But high-resolution observations from the Hubble Space Telescope ultimately settled the argument, revealing the telltale signs of a supermassive black hole weighing in at around 1 million solar masses. Now, a million solar mass black hole is not itself record-breaking. What makes it an anomaly is its home. Henize 210 is a dwarf galaxy, only about 1/10 the diameter of the Milky Way and forming stars at a ferocious rate. According to the established scaling relations, a galaxy of its size and type should host a central black hole that is thousands of times smaller, if it has one at all. Instead, it possesses a gravitational titan. This discovery forces a complete re-evaluation of how black holes form and grow in the early universe. The standard model of co-evolution suggests that black holes grow in lockstep with their host galaxies, primarily through mergers. But a dwarf galaxy like Henize 210 is unlikely to have undergone the series of major mergers required to build such a massive black hole under that model. So how did it get there? Astronomers are exploring two fascinating and revolutionary possibilities. The first is that these overmassive black holes are not the products of later growth, but are instead primordial remnants, direct collapse black holes from the very dawn of time. In this scenario, in the chaotic first few hundred million years after the Big Bang, immense clouds of pristine gas could have collapsed directly into a black hole with a mass of tens or even hundreds of thousands of suns, skipping the star phase entirely. These seeds would then be planted, fully formed, into the infant protogalaxies that would later become dwarfs. They wouldn't need to grow much, they started out big. The second possibility is that these black holes had a uniquely violent and efficient feeding history within their small galaxies. In a large galaxy, a growing black hole is often stifled by its own energy output. Radiation and jets from its accretion disk blow away the surrounding gas, starving itself and regulating its growth. But in a dense, gas-rich dwarf galaxy, the conditions might be just right for a black hole to feast almost unimpeded, gorging on gas and rapidly swelling to a size that defies its environment. This could be a runaway process, where the very turbulence of rapid star formation in a dwarf galaxy funnels material directly into the waiting gravitational grasp of the central black hole, allowing it to become supermassive far more quickly than the galaxy itself can grow. The presence of such a massive black hole in a dwarf galaxy isn't just a curiosity, it has profound implications. Its powerful gravity can influence star formation across the entire galaxy, potentially triggering or quenching the birth of new stars. It acts as a miniature, hyperactive version of the engines seen in distant quasars, a proof of concept that you don't need a giant galaxy to host a giant black hole. This imbalance is more than a statistical outlier. It's a direct challenge, urging us to rewrite the story of black hole genesis and acknowledge that the pathways to cosmic power are far more diverse and unexpected than we ever imagined. Just when we thought we had a handle on the strange and ethereal nature of ultra-diffuse galaxies, the universe presented us with an anomaly so shocking it seemed to pull the very rug out from under modern cosmology. For decades, one principle has been considered as fundamental to our understanding of the cosmos as gravity itself. That dark matter is the invisible scaffolding of every galaxy. This mysterious substance, which does not emit, absorb, or reflect light, is believed to make up over 80% of all matter in the universe. It's the gravitational glue that holds galaxies together, the essential ingredient that allows them to form in the first place and prevents them from flying apart as they spin. Every galaxy we've ever studied, from the mightiest ellipticals to the smallest dwarfs, has shown the unmistakable gravitational signature of being dominated by this unseen mass. It is the cornerstone of the Lambda CDM model, the very foundation upon which our entire cosmic rulebook is built. So, what happens when we find a galaxy that appears to break this most sacred rule? Enter NGC 1052 DF2, a galaxy that sent shockwaves through the astronomical community upon its detailed study in 2018. DF2 is what's known as an ultra-diffuse galaxy, similar to Dragonfly 44, but with one Earth-shattering difference. When a team led by astronomer Pieter van Dokkum measured the velocities of its star cluster's 10 faint, fuzzy balls of stars orbiting the galaxy's main body, they expected to see them whizzing around at high speed, held in place by the powerful grip of a massive dark matter halo. Instead, they found something that seemed almost impossible. The clusters were moving slowly, almost lazily. Their speeds were so low that when the researchers calculated the total mass required to keep them bound to the galaxy, it matched almost exactly the mass of the stars and gas they could see. There was no room left for dark matter. In a universe where dark matter is supposed to be the dominant player, NGC 1052 DF2 appeared to be made of nothing but the ordinary, visible stuff. It was like finding a towering skyscraper that somehow defied gravity, yet upon inspection, you discovered it was built without any steel framework, just the glass and drywall standing tall against all expectations. The immediate reaction, as with any finding that challenges a core paradigm, was intense skepticism. Could this be a simple error in measurement? Perhaps the galaxy is oriented in such a way that we're not seeing the true motion of the clusters. Or maybe it's much closer or farther away than we think, throwing off all the calculations. The team, including researchers like Shani Daniley, have tirelessly worked to rule out these alternatives. Follow-up observations with the Keck Observatory and the Hubble Space Telescope have only reinforced the initial conclusion. They even found a second galaxy in the same category, NGC 1052 DF4, which shows the same startling lack of dark matter. This made it harder to dismiss as a one-off fluke. The evidence is mounting that these galaxies are real, and their existence forces us into a corner where we must ask profoundly difficult questions. Did these galaxies somehow form without dark matter to begin with, or did they have it and then have it brutally ripped away? This is where the mystery deepens from a simple oddity into a fascinating cosmic detective story. Both of these dark matter-deficient galaxies are located near a massive elliptical galaxy called NGC 1052. One compelling theory suggests that they were once normal dwarf galaxies, each with its own dark matter halo that ventured too close to this giant. In a process called tidal stripping, the immense gravitational tide from NGC 1052 could have torn away their dark matter while leaving the more tightly packed stars relatively unscathed. It's a galactic version of a theft where the thief only steals the invisible scaffolding, leaving the visible building oddly intact. However, this explanation is not without its own problems. The simulations of such interactions are messy and often leave clear tidal debris streams of stars stretching out into space, which we don't strongly see around DF2 and DF4. Furthermore, the star clusters in DF2 are old and calm, showing no signs of the violent disruption such a traumatic event would likely cause. This leaves open the door for even more radical possibilities. Could our understanding of gravity itself be incomplete on galactic scales? This is the territory of theories like modified Newtonian dynamics, or MUND, which proposes that what we attribute to dark matter is actually a modification of the laws of gravity at very low accelerations. While MUND has had some success explaining certain galactic rotation curves, it struggles with the specific case of DF2. Its predictions don't neatly align with the observed motions there either. Alternatively, perhaps dark matter is even more bizarre than we thought, possessing properties that allow it to interact with itself or with normal matter in ways we haven't yet dreamed of, creating scenarios where it can be separated from the stars it is supposed to anchor. The existence of these seemingly impossible galaxies is not a death knell for dark matter. Instead, it is a powerful catalyst. It pushes our models to be more nuanced, more creative. It tells us that galaxy formation is not a single monolithic process, but a diverse set of pathways with different outcomes. The discovery of NGC 1052 DF2 and its kin is a brilliant reminder that the universe is under no obligation to conform to our textbooks. It dares to create structures that defy our most basic assumptions, and in doing so, it guides us toward a deeper, more complete truth. The absence of the invisible in these galaxies is perhaps one of the most significant clues we have, pointing toward unforeseen and thrilling new chapters in the story of cosmic evolution. While we often marvel at the colossal galaxies that anchor bustling urban centers of the cosmos, the universe holds an even deeper secret in its quiet, empty suburbs. Conventional wisdom tells us that true galactic giants, the behemoths housing trillions of stars and supermassive black holes, are products of a privileged upbringing. They are meant to form in the dense, crowded environments of galaxy clusters, where frequent mergers and bountiful gas supplies provide the raw materials for runaway growth. It's a cosmic version of a metropolis where the richest and largest structures naturally develop at the busiest intersections of the cosmic web. But what do we make of a magnificent giant that chooses to live alone in the middle of a cosmic desert, far from any such nourishing environment? This is the perplexing reality of isolated monstrous galaxies, and a prime example is the elliptical giant NGC 1600. Located nearly 200 million light-years away, this galaxy is a titan, with a stellar mass rivaling some of the most famous galaxies in the much denser Virgo or Coma clusters. Yet, NGC 1600 is the dominant member of a small, sparse group of galaxies, a sleepy rural town compared to the sprawling megacities we expect such giants to inhabit. Its most astonishing feature is a supermassive black hole at its core, a gravitational monster weighing 17 billion times the mass of our Sun, one of the most massive black holes ever discovered. This presents a direct challenge to our models. How could a galaxy in such a resource-poor environment acquire enough material, through either mergers or accretion, to build not only an enormous population of stars, but also to feed a black hole of such staggering proportions. The solitude of this giant suggests that our understanding of galactic growth is missing a key ingredient. Astrophysicists grappling with this paradox have proposed several compelling theories. One leading idea is that NGC 1600 is not truly a lone giant, but rather a cosmic cannibal, the last galaxy standing after a dramatic history of mergers within its group. In this scenario, this region of space was once much denser long ago, home to a rich family of galaxies that slowly, over billions of years, merged together. NGC 1600 would have been the central, dominant galaxy, gravitationally consuming all of its smaller neighbors in a series of mergers. This would have funneled a vast amount of gas and stars into its core, fueling tremendous star formation and gorging its central black hole. Once the feast was over, it would have been left as the sole remnant, a bloated giant in a now empty field, with the faint tidal streams of its devoured companions having long since faded from view. This would be a case of isolation being a recent state, the calm after a storm of violent galactic interactions. Another fascinating possibility involves a different mode of growth altogether: quiet, cold accretion. Instead of the violent, merger-driven feasting, perhaps NGC 1600 learned to dine with precision. It might have possessed the unique ability to steadily and efficiently siphon cool gas directly from the faint filaments of the cosmic web that thread through even low-density regions. This continuous trickle of fuel over many billions of years could have allowed for sustained internal star formation and a very efficient feeding of the central black hole, enabling it to grow to an enormous size without the need for dramatic, disruptive merger events. This method of growth is more subtle and far less messy, potentially leaving behind a very different structural signature in the galaxy than the chaotic aftermath of major collisions. The existence of these isolated titans forces a significant revision of the simple notion that environment is destiny for galaxies. It reveals that while dense environments can accelerate galactic evolution, they are not the only path to greatness. There must be hidden drivers, perhaps related to the initial conditions of the dark matter halo that a galaxy forms within, or the specific timing and manner of its gas accretion, that can allow a galaxy to achieve monstrous proportions against all environmental odds. These lone giants stand as monumental exceptions to the rule, proving that the universe has more than one recipe for building a colossus, and that true cosmic power can sometimes flourish in the most unexpected and quietest of places. Traveling back in time to the universe's infancy, we expect to find a chaotic, violent nursery, a place of clashing proto-galactic blobs, rampant star formation, and swirling, turbulent gas where nothing is settled. In these first few billion years after the Big Bang, the cosmos should be a construction zone, a primordial mess where the elegant structures we see today are only just beginning to assemble themselves. This is what our most sophisticated simulations, running on some of the world's most powerful supercomputers, consistently tell us. It takes time, a lot of it, for the frantic energy of the young universe to settle down. Gas needs to cool, angular momentum needs to be redistributed, and galaxies need to experience a series of mergers that gradually sculpt them into the stable, rotating disks we know so well. According to the established timeline, a well-ordered, massive disk galaxy like our Milky Way should be a product of a mature universe, taking perhaps 9 or 10 billion years to achieve its graceful form. So, the discovery of such a galaxy existing when the universe was a mere 1.5 billion years old, a toddler by cosmic standards, is nothing short of revolutionary. This is the story of the Wolf Disk, officially known as DLA 0817+1721, a galaxy so profoundly out of place in time that it forces us to question the very clockwork of galactic evolution. Revealed in stunning detail by the Atacama Large Millimeter Array, or ALMA, this galaxy was already a fully formed, massive, rotating disk of gas when the universe was only 10% of its current age. It wasn't a clumpy, disorganized proto-galaxy. It was a settled, mature system, calmly spinning with a mass of over 70 billion suns, its rotation providing the stability needed for efficient star formation. The existence of the Wolf disk creates a glaring tension between observation and theory. Our models struggle immensely to produce such a massive, cold, ordered disk so early. The problem is one of cooling and turbulence. In the hot, dense early universe, gas is incredibly energetic. For it to collapse and form a thin, stable disk, it must be able to radiate away its thermal energy very efficiently. The simulations suggest this process should be slow, hindered by frequent mergers that constantly stir up the gas, preventing it from settling into a quiet, organized rotation. The Wolf disk and other early disks like it are living proof that the universe found a way to fast-track this process, achieving in a blink of cosmic time what we thought should take an eon. Astronomers studying this profound anomaly, like Marcel Nieleman, who led the team that discovered the Wolf disk, have emphasized just how disruptive this finding is to our standard playbook. He noted that most galaxy formation models require galaxies to go through a much more chaotic and violent period before they settle into a stable rotation. They simply need more time to get their act together. The presence of the Wolf disk so early in cosmic history suggests that the early universe was far more capable of creating order from chaos than we ever believed. It implies that the physical processes governing gas cooling, accretion, and angular momentum were operating with a startling efficiency that our current simulations fail to capture. Perhaps the gas was able to cool much more rapidly through pathways we haven't considered, or maybe the accretion of gas onto these young galaxies was exceptionally smooth and cold, flowing in along thin filaments without the disruptive turbulence caused by major mergers. This isn't just a minor adjustment to the timeline. It's a fundamental challenge that points to a gap in our understanding of physics itself during the universe's most formative years. The implications of this premature maturity ripple outward, touching on one of the grandest questions in all of astronomy: how galaxies get their shape. The serene existence of the Wolf disk suggests that the classic Hubble sequence of galaxy morphology, the elegant classification of spirals and ellipticals, may have been established incredibly early. The universe didn't have to wait to make beautiful, structured galaxies. It was making them from the very beginning. This forces a complete re-evaluation of the conditions in the early cosmos. Was it calmer than we think? Or were the mechanisms for creating stability far more powerful and effective? This early sophistication is a direct hint that there are unknown physical processes at work, processes that allowed galaxies to find a state of graceful equilibrium amidst the primordial frenzy, setting the stage for everything that was to come. But the universe's capacity for contradiction doesn't stop at entire galaxies moving against the grain. It delves deep into their very hearts, creating internal conflicts that defy the most fundamental principles of motion. We intuitively understand that when a single object spins, all its parts work in concert. A spinning figure skater pulls their arms in to accelerate, a principle rooted in the conservation of angular momentum, a fundamental law of physics that says the total spin of an isolated system must remain constant. We expect galaxies to follow this same elegant rule, with their stars, gas, and dark matter all rotating together in a grand, unified dance that has persisted since the moment of their formation. So, the discovery of galaxies where this harmony is completely shattered is not just surprising, it feels physically impossible. Imagine a colossal whirlpool where half the water spins clockwise while the other half churns counterclockwise. This is the reality of galaxies with counter-rotating components, cosmic structures locked in a perpetual internal struggle that, by all rights, should have torn them apart billions of years ago. A stunning example of this celestial paradox is the lenticular galaxy NGC 4550, located in the heart of the Virgo cluster. At first glance, it appears as a fairly normal, fuzzy ellipse of light. But when astronomers trained powerful spectrographs on it, they were able to measure the velocity of its individual stars along our line of sight. The data revealed something astonishing. Roughly half of the stars in its disk are orbiting the galactic center in one direction, while the other half are moving in the exact opposite direction. These two populations of stars are intermingled, sharing the same space yet moving in a direct opposing ballet. It's a configuration that seems inherently unstable, a recipe for constant gravitational friction and chaos that should have long since disrupted the galaxy's delicate structure, causing it to either dissolve into a formless ellipsoid or triggering a massive burst of star formation from the colliding gas clouds. Yet there it is, a serene-looking galaxy that has somehow maintained this bizarre internal conflict for eons. The existence of such a system throws a massive wrench into our standard theories of how galaxies assemble themselves. The most straightforward explanation for counter-rotation is a galactic merger. If a smaller galaxy approaches a larger one from the opposite direction of its rotation and is consumed, its stars could, in principle, end up orbiting backwards. However, mergers are incredibly violent events. They blast through a galaxy like a gravitational hurricane, violently stirring up gas, triggering immense starbursts, and completely erasing any delicate disk structure, typically leaving behind a puffed-up elliptical galaxy. NGC 4550, by contrast, still maintains a distinct disk. It shows no signs of the recent, violent trauma that a major merger would inflict. This forces astronomers to consider more gentle, subtle mechanisms for this cosmic contradiction. One leading theory is a process called gas accretion. Imagine a vast, lone cloud of pristine hydrogen gas, perhaps a remnant from the early universe, slowly drifting through intergalactic space. If this cloud were to be captured by a galaxy's gravity, but it happened to be moving in a retrograde orbit opposite to the galaxy's rotation, it could slowly, over billions of years, drip onto the existing disk. This gas would then cool and collapse to form new stars, but these newborn stars would inherit the motion of the incoming gas cloud, thus establishing a new generation of stars that spin in the opposite direction to their older siblings. This is a far more peaceful and gradual process than a merger, one that could potentially build a counter-rotating disk without destroying the galaxy's overall coherence. Another fascinating idea involves the complex dynamics of a galaxy's dark matter halo. If the halo itself has a misaligned spin, it could gradually torque the incoming gas and influence the orbital directions of stars in ways we are only beginning to model. The persistence of these counter-rotating systems is perhaps the deepest part of the mystery. Why doesn't dynamical friction, the gravitational drag between objects moving through each other, cause these opposing streams to slow down, merge, and erase the contradiction? The fact that they haven't suggests that the galaxy has found a precarious yet stable equilibrium. It's possible the two populations are orbiting at slightly different inclinations, like two great gears meshing without touching, minimizing direct interaction. Or perhaps the galaxy's overall gravitational potential is smooth enough that the stars simply pass through each other like ghosts. their interactions too weak to significantly alter their opposing motions over cosmic time. This internal discord is far more than a curiosity. It is a direct challenge to our grasp of galactic dynamics, revealing that the processes of accretion and internal evolution are far more nuanced and capable of producing stable, yet profoundly strange, configurations than our simulations have yet been able to reproduce. After exploring galaxies locked in internal conflict, we now turn to a cosmic paradox of a different kind: structures that possess all the ingredients for creation, yet remain shrouded in darkness. Picture a vast reservoir of primordial gas, swirling within the gravitational embrace of a dark matter halo, containing enough raw material to birth billions of stars. This should be a brilliant beacon, a factory of light and heat, but when we point our telescopes toward it, we see almost nothing, a profound silence. This is the eerie realm of dark galaxies, invisible stellar nurseries that defy one of the most fundamental processes in the universe, the ignition of stars. These enigmatic objects are detected not by the light they emit, but by the faint radio whispers of their atomic hydrogen gas. Using powerful radio telescopes like Arecibo or the Very Large Array, astronomers can map the distribution of this neutral hydrogen through its characteristic 21-centimeter wavelength emission. One of the most famous candidates is HI 1225+01, a vast cloud of gas found in the Virgo cluster with the mass of a small galaxy, but emitting less than 1% of the expected starlight. It's like finding a fully stocked library with endless shelves of books, but no one inside to read them, a treasure trove of potential that remains almost entirely untapped. The existence of such objects directly challenges our understanding of star formation efficiency. According to our standard models, a gas cloud of that density and mass should have long ago undergone gravitational collapse, fragmenting into dense cores that ignite into stars. The fact that it hasn't forces us to ask what powerful mechanism is putting a cosmic lid on this natural process, preventing the spark of creation in a seemingly perfect environment. Astrophysicists like Michel Bellet are at the forefront of unraveling this mystery, proposing several compelling theories for why these galaxies remain dark. One leading idea is that they are primordial relics, fossil clouds from the early universe that have managed to avoid the major mergers and interactions that typically trigger star formation. In this scenario, a dark galaxy could be a pristine pocket of gas that has drifted through cosmic time in exceptional isolation, its gas too diffuse and its gravitational field too weak to initiate the collapse needed to form stars. It's a sleeping giant waiting for an external jolt, perhaps a close encounter with another galaxy, to finally awaken it. Another, more dynamic explanation involves powerful internal feedback mechanisms that actively suppress star birth. Imagine that within this vast gas cloud, a first generation of stars did indeed begin to form. These first stars would have been massive, hot, and short-lived, exploding as supernova within a few million years. These violent explosions would have unleashed tremendous energy, heating the surrounding gas and driving powerful winds that blew the remaining star-forming material right out of the galaxy. Without dense, cool gas to collapse, star formation would effectively be shut down, leaving behind a ghostly, gas-rich husk that is incapable of making new stars. This is a case of a galaxy effectively committing stellar infanticide, where its own first-born stars destroy any chance for siblings to follow. A third, fascinating possibility involves the very nature of the dark matter halo itself. Perhaps the dark matter in these systems is distributed in a way that creates a particularly shallow gravitational potential well. In a normal galaxy, the deep gravity well helps to compress gas and hold onto it. In a shallow well, the gas may never reach the critical densities needed for collapse, or it may be easily stripped away by even faint intergalactic tides or the pressure of the thin gas that permeates the space between galaxies. The silence of these dark galaxies is not an absence of activity, but a clue to a complex and delicate balance of forces. They represent a road not taken in galactic evolution, showing us that the journey from gas to stars is not inevitable. It can be delayed, suppressed, or even prevented altogether by a variety of environmental and internal factors, revealing a much wider and more diverse spectrum of galactic existence than we ever thought possible. Just as the silent darkness of gas-rich galaxies presents one kind of cosmic puzzle, the universe offers a starkly opposite enigma: galaxies that shine with a chemical signature far too mature for their modest stature. We often think of cosmic evolution in terms of size and mass, but there is another, more subtle history written in the elements themselves, a story of stellar life and death that forges heavier atoms and seeds them back into space. This process, called chemical enrichment, is thought to follow a predictable path. Larger galaxies, with their deeper gravitational wells and more frequent stellar cataclysms, become metal-rich over time, while smaller dwarf galaxies, with their gentler star formation, should remain relatively pristine, cosmic backwaters of primordial gas. This is why the discovery of certain dwarf galaxies boasting unexpectedly high concentrations of heavy elements or metallicity is so deeply confounding. It's like finding a small, isolated village that somehow possesses the advanced technology of a sprawling metropolis, forcing us to question how it acquired such sophisticated resources against all odds. This anomaly strikes at the very heart of galactic archaeology, the science of reading a galaxy's history through its elemental composition. In astronomy, metals refer to any element heavier than hydrogen and helium: the carbon in our bodies, the oxygen we breathe, the iron in our blood. These elements are not born in the Big Bang. They are forged exclusively in the nuclear furnaces of stars and scattered across the cosmos in their violent supernova deaths. A galaxy's metallicity is therefore a direct measure of its stellar history, a ledger recording how many generations of stars have lived and died within it. For a small, faint dwarf galaxy, which typically has a shallow gravitational potential and a low star formation rate, this ledger should show only a few entries. They simply haven't had the continuous, vigorous cycles of star birth and death required to cook vast amounts of primordial hydrogen and helium into heavier elements. The metal content in their stars and gas should be low, yet in galaxies like Zwicky 18, a blue compact dwarf, we find a metallicity that is startlingly high for its size and youthfulness, completely upending the standard timeline of chemical evolution. Unraveling this puzzle leads astronomers down several fascinating and complex paths. One compelling theory is that of a dramatically accelerated, or bursty, star formation history. Imagine a typically quiet dwarf galaxy that suddenly, and for reasons not entirely clear, experiences an incredibly intense, rapid-fire burst of star formation. This isn't just a gentle period of activity, it's a veritable firestorm of stellar birth. In this ferocious environment, massive stars are born in huge numbers. These stars live fast and die young, exploding as supernova within just a few million years, a blink of an eye on cosmic timescales. Each supernova acts as a colossal chemical factory, ejecting newly forged heavy elements at tremendous speeds into the surrounding gas. This creates a powerful feedback loop. The enriched gas from the first wave of supernova collapses under its own weight, triggering a second, even more metal-rich generation of stars. This cycle can repeat in a frantic, self-amplifying chain reaction, allowing a small galaxy to achieve a level of chemical maturity in a relatively short period that would normally take a much larger galaxy billions of years of steady evolution to accomplish. Another intriguing possibility is external pollution, a galactic case of a wealthy neighbor moving in next door. Perhaps these metal-rich dwarf galaxies were not always so isolated. They could have once been satellites orbiting a much larger, more evolved host galaxy. Over billions of years, they might have been showered with metal-enriched gas stripped from their larger companion through tidal forces or through the vast, gaseous winds driven by the host galaxy's own supernova. This would be a form of cosmic inheritance, where the dwarf galaxy gains its high metallicity not through its own efforts, but by accreting pre-enriched material from its environment. There's also the dramatic possibility of a dwarf-dwarf galaxy merger. While less violent than collisions between giant galaxies, the merger of two smaller systems could funnel their collective gas reservoirs together, igniting a powerful starburst and efficiently mixing their already processed metals, creating a new composite galaxy that is chemically far more advanced than either of its progenitors. The implications of these metal-rich anomalies extend far beyond the galaxies themselves. They force a refinement of our models for the entire cosmic cycle of life and death. The rate at which stars form and die, and how efficiently they pollute their surroundings, is a key parameter in simulations of the universe's evolution. These dwarf galaxies are telling us that our models might be too simple, that star formation can be far more efficient and explosive in small systems than we thought, or that the transfer of material between galaxies plays a much more significant role in chemical enrichment than previously believed. They serve as crucial reminders that a galaxy's history is not written solely in its stars and mass, but also in the intricate elemental fingerprints that reveal a past potentially filled with sudden, violent bursts of creativity and unexpected relationships with its cosmic neighbors. Just when we think we've catalogued every type of star system, the universe reveals another class of object that defies our neat classifications, blurring the lines between what we know and what we thought was possible. Tucked away in the halos of massive galaxies and within rich clusters, astronomers have discovered tiny, enigmatic specks of light that at first glance resemble simple globular clusters, those ancient spherical collections of stars that orbit galaxies like bees around a hive. But upon closer inspection, these specks revealed themselves to be something far more extraordinary and perplexing: ultra-compact dwarf galaxies, or UC. Imagine taking a galaxy like the Large Magellanic Cloud, which spans 14,000 light-years, and crushing it down into a sphere only 200 light-years across. The result would be an object of almost unimaginable density, a cosmic bullet packing tens of millions of stars into a volume so small it appears as a single, star-like point in most telescopes. This is the bizarre reality of UCDs, and their discovery has forced a complete rethinking of the boundary between giant star clusters and the smallest galaxies. The story of their discovery is a classic tale of scientific serendipity. In the late 1990s, two independent teams were conducting a survey of galaxies in the nearby Fornax cluster, a dense gathering of galaxies about 60 million light-years away. Using the powerful new digital cameras on large telescopes, they were looking for faint, diffuse dwarf galaxies. Instead, they kept finding these strange, extremely compact objects that were far brighter than any known globular cluster, yet far too small to be a typical dwarf galaxy. They were, as one astronomer put it, objects that looked like stars but couldn't be stars. Initially dismissed as foreground stars or camera artifacts, their true nature was only revealed through spectroscopy, which showed their light was the combined glow of millions of ancient stars, all moving together as a single, gravitationally bound system. The first identified UCD, now known as UCD3 in the Fornax cluster, was 100 times more massive than the most massive globular cluster known, yet only a tenth the size of a typical dwarf elliptical galaxy. It occupied a no-man's land in the mass-size diagram, a place where no objects were predicted to exist, and its discovery immediately launched a fierce debate about its origin. This debate centers on two compelling, yet opposing, theories for how these dense powerhouses came to be. The leading explanation is the threshing or striping scenario. In this dramatic model, UCDs are not born as ultra-compact objects. They are the surviving, naked hearts of what were once much larger galaxies. The story goes that a small but normal dwarf elliptical galaxy ventured too close to the immense gravitational field of a giant galaxy in the cluster's center. As it made repeated passes, the tidal forces, the difference in gravity between the side of the dwarf closest to the giant and the side farthest away, acted like a cosmic threshing machine. These forces brutally stripped away the dwarf's outer layers of stars and dark matter, leaving behind only its dense central nucleus. This nucleus, now orphaned from its original galactic body, continues to orbit the giant galaxy as an ultra-compact remnant of its former self. This theory is powerfully supported by the discovery of a few objects that appear to be transitional, caught in the act of being stripped, with faint streams of stars still trailing away from them. The second major theory argues that at least some UCDs could be supermassive globular clusters, born in isolation through a process we don't yet fully understand. Globular clusters are thought to form during major, gas-rich merger events in a galaxy's history. Perhaps during the most extreme mergers in the early universe, conditions were right to form globular clusters on steroids, clusters that started out with much more mass and a much larger number of stars than any we see forming today. These primordial superclusters would have simply lived on as ultra-compact fossils from a more violent time. The evidence for this is that the very brightest UCDs seem to follow a scaling relation that connects them smoothly to the population of normal globular clusters, suggesting they might be the high-mass end of the same family. The plot thickens considerably when we consider the dark matter content, which is the real key to distinguishing a true galaxy from a mere star cluster. Globular clusters, for all their stars, are believed to contain very little to no dark matter. Their gravity is dominated by the visible stars. True dwarf galaxies, even tiny ones, are dominated by massive halos of dark matter. So, where do UCDs fall? This has proven to be one of the most difficult questions to answer. Measuring the mass of something so small and distant is an immense challenge. Some studies, which measure the mass through the motion of stars within the UCD, suggest that the most massive ones have more mass than can be accounted for by their stars alone, hinting at the presence of dark matter, a strong indicator of a galactic origin. Other studies have found no such evidence, concluding that their mass is consistent with stars alone, pointing to a cluster origin. This contradiction suggests that UCDs may not be a single class of object at all, but rather the final destination for multiple evolutionary pathways. Some could be the stripped nuclei of galaxies, and thus might still harbor a significant amount of dark matter, while others could indeed be monster globular clusters that never had any dark matter to begin with. The existence of these dense mysteries challenges our very definitions. They force us to ask, what is the minimum requirement for a galaxy? Is it the presence of dark matter? Is it a complex evolutionary history? Or is it simply a gravitationally bound collection of stars above a certain mass? UCDs sit squarely on this fuzzy boundary, serving as a perfect laboratory to study the extremes of gravity and stellar dynamics. Their incredible density means that stellar interactions are far more frequent than in a normal galaxy, potentially leading to exotic objects like an abundance of black hole binaries or rapidly spinning millisecond pulsars. They are natural crucibles for testing the limits of how stars behave in crowded conditions. Each ultra-compact dwarf is a compact puzzle, a tiny, brilliant point of light that contains a massive story of gravitational struggle, cosmic violence, and the enduring mystery of how structures great and small find their place in the universe. If the serene counter-rotation of stars presents a puzzle of internal conflict, then the next anomaly reveals a far more fundamental and invisible disconnect, a profound misalignment between a galaxy and its own hidden skeleton. Our standard picture of galaxy formation is one of harmonious growth, a graceful ballet where the visible disk of stars and gas spins in perfect concert with the immense, invisible dark matter halo that cradles it. This co-rotation is a natural prediction of the dominant lambda CDM model. As a galaxy forms through the hierarchical merging of smaller structures, the collective angular momentum from these mergers is thought to imprint a consistent spin on both the visible and the dark components. They are born together and they should spin together, but the universe in its infinite complexity loves to break its own rules, presenting us with galaxies where this fundamental harmony is entirely absent, creating a gravitational framework that is fundamentally twisted. A stunning and deeply studied example of this cosmic misalignment is the blue compact dwarf galaxy NGC 2915. From the outside, it looks like a fairly typical small galaxy, but it holds a secret that only precise measurements can reveal. Observations of its neutral hydrogen gas, which extends far beyond its visible stellar disk, allow astronomers to map its rotation with incredible detail. Meanwhile, the motion of its stars and the gravitational forces at play provide clues to the behavior of its dark matter halo. The data paints a startling picture. The rotation of the vast, extended gas disk is significantly misaligned with the inferred spin axis of the dark matter halo that ostensibly governs its motion. It's as if the galaxy's visible body is spinning on a different tilted axis than its invisible gravitational anchor, creating a system that is fundamentally off-kilter. This isn't a minor wobble, it's a deep-seated contradiction that challenges the very idea of a unified, coherent formation process. Astrophysicists grappling with this paradox point to two primary culprits, both involving a violent and chaotic past. The first is a history of chaotic gas accretion. Imagine that long after its initial formation, NGC 2915 began to feast on cold streams of intergalactic gas. But this cosmic rainfall did not arrive in an orderly fashion, aligned with the galaxy's existing rotation. Instead, these gas streams may have come in from random, oblique angles, perhaps from multiple directions over time. As this new gas, carrying its own angular momentum, piled onto the existing disk, it could have gradually torqued and twisted the orientation of the visible material, slowly slewing it away from the original spin direction established by the dark matter halo billions of years earlier. The dark matter, being more diffuse and less responsive to these late-stage gas inflows, would have largely retained its original spin, leaving the two components permanently out of sync. The second explanation involves a more dramatic event, a past interaction or a near miss with another galaxy. Even without a direct collision, a close gravitational encounter can exert a powerful tidal force, a kind of cosmic torque that can wrench the disk of stars and gas, altering its rotational plane. It's like giving a spinning top a sharp, glancing flick. Its axis of rotation can be suddenly and dramatically changed. The dark matter halo, being more extended and less centrally concentrated, would be far less affected by such a brief interaction, remaining largely in its original orientation. This would create the exact kind of misalignment we observe. However, the real mystery is not just how this misalignment began, but how it has managed to persist for billions of years. According to our understanding of gravity and dynamics, such a configuration should be unstable. We would expect a process called dynamical friction to act as a cosmic dampener. The gravitational drag between the misaligned visible disk and the dark matter particles in the halo should, over time, cause the disk to slowly realign itself with the halo's equatorial plane, erasing the discrepancy. The fact that we see galaxies like NGC 2915 still maintaining their twisted state suggests that this damping process is far less efficient than our models predict, or that some ongoing mechanism is actively maintaining the misalignment. This persistence is the most tantalizing part of the puzzle, pointing directly to gaps in our understanding of dark matter itself. Perhaps dark matter particles possess properties that make them far less effective at exerting this kind of gravitational drag than we assume. Maybe they can stream through the visible disk with minimal interaction, like a ghost passing through a wall, offering little resistance to its misaligned spin. Or perhaps the halo itself is not the smooth, symmetric structure we typically model it as, but is instead lumpy or triaxial, with a complex and shifting gravitational field that can somehow lock in a misaligned disk state. The existence of these twisted systems forces us to consider that the assembly of a galaxy is not a single, monolithic event that establishes a permanent order, but rather a continuous and often chaotic process where different components can have their own separate histories and where stability can be found in seemingly unbalanced configurations. Returning to the celestial bullseye of Hoag's object, we are confronted with a formation so pristine and isolated that the classic collision narrative begins to fray at the edges. This is the peaceful formation puzzle, a challenge to the notion that such perfection requires cosmic violence. If a direct impact didn't sculpt this ring, what gentle, internal forces could possibly be responsible for such a flawless geometric arrangement? Astrophysicists have begun to explore a suite of alternative mechanisms that operate on timelines of billions of years, not millions, suggesting a more patient and subtle form of cosmic artistry. One compelling theory revolves around the concept of resonant density waves. In this scenario, the graceful ring is not the result of a sudden shockwave, but rather a slowly propagating rhythm, a gravitational harmonic that organizes the galaxy's material. Imagine the entire galactic disk as a vast, fluid membrane. Specific orbital resonances points where the gravitational tug from the central bulge and the disk itself create a stable, repeating pattern, can act like a cosmic loom, weaving gas and stars into a coherent ring structure. It's a process not unlike the one that forms the beautiful spiral arms of galaxies like our own Milky Way, but taken to a more extreme and stable conclusion. This mechanism could potentially create a long-lived ring without any external trigger, a testament to the innate musicality of gravitational physics. Another internal process under investigation is known as secular evolution, driven by instabilities within the galaxy itself. A central bar of stars, a common feature in many disk galaxies, can act as a powerful engine for redistributing a galaxy's mass. Over immense timescales, this bar can slowly dissolve, transferring its angular momentum to the outer disk. This process effectively pushes gas outward, funneling it to a specific resonance radius where it piles up, becomes dense, and ignites a brilliant circle of new star formation. The bar itself may eventually vanish, leaving behind the ring as the only evidence of its former existence and its slow, steady work. This provides a pathway to a ring galaxy that is entirely self-made, a product of its own gradual and majestic evolution. The sheer rarity and beauty of these objects, as noted by many researchers, underscores just how special the conditions for their formation must be. This has led to even more exotic proposals that venture beyond conventional gravity. Could the mysterious influence of dark matter play a role? Perhaps an unusual, lopsided distribution of dark matter within the halo could gravitationally torque the gas disk, coaxing it into a ring-like configuration without the need for a single flyby or collision. Or, borrowing a concept from particle physics, could something like spontaneous symmetry breaking occur on a galactic scale? In this idea, the initially uniform disk undergoes a phase transition, a sudden shift that breaks its symmetry and causes it to settle into a new, lower energy state, the stable ring and core structure we observe. This peaceful formation narrative dramatically expands our view of galactic morphology. It reveals that the universe is capable of creating its most stunning structures not only through catastrophic collisions, but also through patient, internal choreography. The existence of Hoag's object and its kin suggests that given enough time and the right conditions, a galaxy can sculpt itself into a work of art, achieving a state of serene equilibrium that stands in quiet defiance of the chaotic cosmos from which it was born. After exploring the serene and patient formation of ring galaxies, we now venture into the chaotic and explosive hearts of galactic cores, where we find a phenomenon that seems to defy the very logic of gravitational destiny. Picture the center of a galaxy, a place where we expect to find a single, terrifying gravitational anchor, a supermassive black hole millions or even billions of times the mass of our Sun. Now imagine that instead of one, there are two brilliant, active nuclei blazing with the light of accreting gas, two monstrous engines of power orbiting one another at the very core of a single galaxy, locked in a gravitational dance that should, by all rights, end in a cataclysmic merger. This is the reality of galaxies with double nuclei, cosmic structures with twin hearts that somehow beat as one for timescales that baffle our understanding. A quintessential and stunning example of this cosmic duality is the galaxy NGC 6240, a chaotic and beautiful mess located about 400 million light-years away. In visible light, it appears as a distorted, butterfly-shaped wreck, a clear testament to a recent and violent galactic collision. But when observed in the infrared and X-ray spectra, its true secret is revealed. Not one, but two intensely bright nuclei, separated by a mere 3,000 light-years. Each of these nuclei is now known to be a supermassive black hole, both actively feeding on the gas and debris stirred up by the colossal merger that brought their host galaxies together. According to our most straightforward models of galactic dynamics, this situation should be highly transient. As the two black holes orbit each other, they are expected to lose energy through a process called dynamical friction, interacting with the surrounding stars and gas and slowly spiraling inward. Their final parsecs together should be a quick, violent plunge, culminating in a universe-shaking burst of gravitational waves as they finally coalesce into a single, larger black hole. Yet, observations suggest that many of these binary systems, including the one in NGC 6240, appear to be stalled, remaining stable for periods far longer than our simulations predict. This longevity presents a profound challenge to our models of black hole coalescence and galactic core evolution. The central question is simple yet deeply troubling. Why haven't they merged? If the merger process is inefficient or can be delayed for billions of years, it would mean the universe is likely teeming with many more of these binary, supermassive black holes than we have yet found, with significant implications for our search for gravitational wave backgrounds. Astrophysicists have developed several compelling theories to explain this stalled fate. One leading idea focuses on the dynamics of the black hole's immediate environment. As they spiral inward, they must gravitationally slingshot away the stars and gas that provide the friction for their inspiral. Once they clear out their immediate vicinity, they may enter what is known as the final parsec problem, where there is simply not enough material left nearby for them to continue losing orbital energy efficiently. They become stranded, two titans in a seemingly endless orbital embrace, unable to get close enough for gravitational radiation to take over and seal their fate. Another fascinating possibility involves the role of powerful feedback effects from the black holes themselves. As each black hole actively accretes matter, it can unleash tremendous outflows of energy and radiation in the form of jets and winds. If these two opposing streams of feedback interact, they could create a turbulent, high-pressure buffer zone between the black holes, effectively pushing them apart and counteracting the inward pull of dynamical friction. It's a cosmic standoff where the very process that makes the black holes visible, their voracious feeding, also provides the force that prevents their ultimate union. The specific orbital configuration also plays a critical role. If the binary orbit is highly eccentric or misaligned with the galactic disk, the efficiency of energy loss can be dramatically reduced, prolonging the merger process to timescales that rival the age of the universe itself. This incredible duality forces us to reconsider the final stages of galaxy evolution, revealing that the core of a merged galaxy can remain a dynamic, binary system for eons, a lasting monument to a violent past that has yet to reach its final, quiet conclusion. After delving into the chaotic hearts of merging galaxies and their stalled binary black holes, we now journey to the opposite extreme of the cosmic landscape, the immense, silent voids. These are the deserts of the universe, vast regions hundreds of millions of light-years across where the average density of galaxies is less than 1/10 of that in the crowded clusters and filaments. According to our most established models of cosmic structure, these are the backwaters, the places where galaxy formation should be stunted, slow, and ultimately unremarkable. The prevailing wisdom of environment-dependent theory is clear. To grow large and active, a galaxy needs to be in a bustling metropolis, where it can feast on gas stripped from neighbors, undergo mergers, and be constantly rejuvenated by the dynamic flow of material along the cosmic web. So, the existence of magnificent, thriving galaxies in the profound emptiness of these voids is not just surprising, it feels like a violation of cosmic zoning laws. A perfect and poignant example of this environmental defiance is the spiral galaxy MCG +01-02-015, often called the loneliest galaxy in the universe. Its name is a catalog number, but its story is one of profound isolation. It resides in a void so immense that if our Milky Way were placed in its position, the nearest comparable galaxy would be 20 times farther away than our own Andromeda neighbor. In this near-total emptiness, one would expect to find only small, quiescent, and faded dwarf galaxies, the cosmic equivalents of isolated ghost towns. Yet, MCG +01-02-015 is a grand spiral, a majestic pinwheel of stars and gas, actively forming new suns and shining with a vitality that belongs in a much richer environment. Its very existence is a direct challenge, forcing us to ask how a galaxy can achieve such grandeur without access to the wealth of resources and interactions found in the crowded urban centers of the cosmos. The unusual properties of these void giants provide the first clues to solving this puzzle. Many of them, contrary to expectations, show enhanced levels of star formation. In the dense environments of clusters, the process of star formation is often harshly quenched. A galaxy falling into a cluster has its gas reservoir stripped away by the intense pressure of the hot intergalactic medium, a process known as ram pressure stripping, leaving it red and dead. But in the serene emptiness of a void, a galaxy exists in a state of peaceful solitude. There is no hot intergalactic wind to blast away its gas, no close gravitational encounters to disrupt its delicate disk. This tranquility allows void galaxies to hold onto their primordial gas for much longer, and in some cases to use it with remarkable efficiency. The star formation may not be explosive, but it can be steady and sustained over much of cosmic history, allowing a void galaxy to gradually build up its stellar mass through a long, quiet, and consistent process of internal conversion. But this alone doesn't fully explain their size. To grow into a true giant, a galaxy needs a massive inflow of fuel. This is where experts propose more exotic mechanisms that might be unique to these barren regions. One compelling theory is that of isolated cold flow accretion. While galaxies in clusters get their gas through the violent and turbulent channels of mergers and interactions, a void galaxy might be fed by a gentle, continuous trickle. Thin, cold filaments of primordial hydrogen gas, remnants from the formation of the cosmic web, could still be threading the void, invisible to our telescopes. A void galaxy, by pure chance, could be sitting at the nexus of a few such faint filaments, receiving a slow and steady supply of fuel directly from the intergalactic medium. This would be a quiet, private meal, uninterrupted for billions of years, allowing the galaxy to grow large in isolation without ever needing to interact with a neighbor. Another fascinating possibility involves the very nature of the dark matter halos that form in these underdense regions. The initial density fluctuations that seeded all structure in the universe would have had a wide range of amplitudes. It's possible that the voids are not completely empty, but are instead home to the rarest of peaks, exceptionally high density fluctuations that just happen to form in an otherwise barren territory. These rare peaks would have collapsed to form unusually massive dark matter halos very early on. A galaxy forming in the heart of such a pristine, massive halo would have a tremendous gravitational advantage from the start, giving it a deep potential well to draw in and retain gas with great efficiency, all while being separated from the chaotic influences of the crowded cosmic cities. Its growth would be driven from within, powered by its own exceptional initial conditions rather than by its environment. The existence of these lonely giants forces a fundamental revision of the simple idea that environment is the sole dictator of a galaxy's fate. It reveals a universe where multiple pathways to greatness exist, one of violent mergers and acquisitions in the clusters, and another of quiet, patient, and isolated accumulation in the deepest voids. For decades, the anomalous rotation of galaxies has been the single most powerful piece of evidence for the existence of dark matter. The story is a cornerstone of modern astronomy. When we measure how fast stars and gas orbit the center of a spiral galaxy, we find that their speeds remain constant or even increase with distance from the core. This flat rotation curve defies the laws of gravity as dictated by Newton and Einstein when applied only to the visible matter. Based on the light we see, those outer stars should be slowing down, drifting away into the void. The only explanation that has held for over 50 years is that every galaxy is embedded within a massive, invisible sphere of dark matter, whose gravitational pull is what keeps those stars whirling at such unexpected speeds. This discovery rewrote the cosmic rulebook, but what happens when we find a galaxy that doesn't just lack dark matter, but whose very rotation seems to mock our predictions, presenting a curve that declines exactly as expected from the visible mass alone? This isn't just an absence of the invisible, it's a direct, brazen challenge to the fundamental premise itself. This is the profound puzzle presented by galaxies like AGC 114,905, an ultra-diffuse dwarf galaxy that has become a flashpoint in one of cosmology's most heated debates. When a team of astronomers led by Pavel Mansour meticulously measured the rotation of its gas using the Very Large Array radio telescope, they expected to see the now familiar signature of dark matter's influence. Instead, they found something that, in the modern cosmological context, is arguably even more shocking. The rotation curve of AGC 114,905 wasn't flat. It declined steadily with distance from the center, following a near-perfect Keplerian decline, just as Newton's laws would predict if only the visible stars and gas were present. It was a curve from a textbook, but from a textbook written before the dark matter revolution. According to everything we think we know, this galaxy should not be able to hold itself together. Its outer gas should be escaping, yet it appears stable. This observation doesn't just suggest a lack of dark matter. It suggests that for this galaxy, the need for dark matter never even arises. The laws of gravity, as we apply them to the visible mass, seem to be sufficient. This single data point throws a wrench into the entire machinery of the lambda CDM model, forcing us into a difficult choice. Either our measurements and assumptions about this galaxy and others like it are critically flawed, or our understanding of gravity itself is incomplete. The scientific community has, understandably, leaned heavily towards the first explanation, proposing a host of potential systematic errors that could create such an illusion. The most prominent critique involves the inclination angle of the galaxy, the tilt at which we view its disk from Earth. If AGC 114,905 is not a nicely tilted, flat disk but is instead almost perfectly face-on, our measurements of the orbital speeds of its gas could be severely miscalculated. A very small error in estimating the inclination could lead to a massive error in calculating the true rotational velocity, potentially making a normal, dark matter-dominated galaxy appear as if it's following purely Newtonian rules. Other proposals suggest that the galaxy might be experiencing significant external pressure from an unseen intergalactic gas medium, which could be artificially confining it, or that it is not in a stable state at all but is in the process of being tidally disrupted, though no obvious culprit galaxy is nearby to do the disrupting. Mansour-Pin's team has vigorously defended their work against these critiques, arguing that they have accounted for inclination to the best of their ability and that the galaxy shows no signs of disruption. This back and forth is the essential, painstaking process of science, but it underscores how a single anomalous observation can shake the foundations of a well-established paradigm. The other, far more radical path of inquiry is to take the result at face value and ask if we are witnessing evidence for modified Newtonian dynamics, or MN. This alternative theory, first proposed by physicist Mordechai Milgrom in the 1980s, suggests that our formulation of gravity is slightly incorrect at the extremely low accelerations experienced in the outer reaches of galaxies. Instead of the force of gravity following the standard inverse square law in these regimes, Mann proposes a new fundamental constant that causes gravity to weaken less rapidly. This single adjustment can beautifully reproduce the flat rotation curves of spiral galaxies without invoking any unseen dark matter. For a galaxy like AGC 114,905, which shows a declining curve, Mann would actually predict that its internal gravitational acceleration is still too high to trigger the modified dynamics, meaning it should behave as if it were in the higher acceleration Newtonian regime, which is exactly what is observed. Proponents of MEND like Stacy McGaw point to this galaxy not as a problem, but as a stunning success of their model's predictive power. In their view, AGC 114905 isn't an anomaly, it's a confirmation. This places the scientific community at a fascinating crossroads. The existence of even a handful of galaxies with such strongly declining rotation curves creates a serious tension within the standard model. It forces a re-evaluation not just of dark matter, but of gravity itself on galactic scales. Are these galaxies the exceptions that prove the rule, their strange spins eventually explained away by subtle astrophysical effects we haven't yet mastered? Or are they the canaries in the coal mine, the first clear sign that our gravitational theories require a fundamental revision that would reshape our understanding of the entire cosmos? The deviation of these anomalous spins is more than a curiosity. It is a direct observational challenge that urges us to look deeper, to question our most basic assumptions, and to remain open to the possibility that the universe's deepest secrets might be hidden not in the darkness we cannot see, but in the fundamental laws we thought we knew. After confronting the enigma of galaxies spinning without the influence of dark matter, we now turn to a cosmic paradox that unfolds not in motion, but in brilliant, unexpected light. If the serene emptiness of cosmic void should be a place of quiet retirement for galaxies, then the discovery of intense stellar firework displays in these very deserts is a shock to the system. We have long understood that the most spectacular bursts of star formation, events so violent they can reshape an entire galaxy, are typically triggered by external chaos, a galactic collision, a close gravitational encounter, or the relentless pressure of a dense cluster environment. These events act as a cosmic kick, compressing vast reservoirs of gas and igniting a ferocious blaze of stellar birth. So, to find a galaxy in the profound isolation of a void, far from any such commotion, suddenly erupting in a starburst of epic proportions, is like finding a single, solitary tree in the middle of an empty field spontaneously exploding into flame. This is the mystery of starburst galaxies in quiescent regions, and it forces us to look for the match that lights the fire not outside the galaxy, but deep within its own hidden workings. Consider the case of a small, isolated dwarf galaxy, adrift in a vast cosmic void. By all accounts, it should be a quiet, fading place. Its star formation, if it has any left at all, should be a mere trickle, a slow and steady process fueled by its dwindling internal gas supply. Yet, observations from telescopes like the Sloan Digital Sky Survey have revealed stunning outliers. These galaxies are undergoing a starburst, a period where they are forming stars at a rate hundreds or even thousands of times faster than a typical galaxy like our Milky Way. They are cosmic cauldrons, forging new suns at a frantic, unsustainable pace that will quickly consume their entire gas reservoir in a mere tens of millions of years, a blink of an eye in cosmic time. The sheer violence of this process is written in their light. They blaze with the intense blue glow of countless massive, young, hot stars and the furious red signature of hydrogen gas heated to a frenzy by their radiation. The paradox is profound. In the emptiness of a void, there are no neighboring galaxies to collide with, no passing giants to exert crushing tidal forces. The standard triggers are absent. As one study of these isolated starbursts noted, they exist in a state of extreme environmental isolation, making their furious activity a clear violation of the established rules of galactic engagement. This glaring contradiction has led astronomers on a hunt for alternative, internal ignition sources, and the suspects are as fascinating as they are elusive. One compelling theory points to the inherent turbulence within the galaxy's own gas supply. Imagine a massive but relatively stable cloud of cold hydrogen gas drifting peacefully within the galaxy's disk. It could be teetering on the edge of gravitational collapse, a delicately balanced system. Then, a seemingly minor event, the powerful shockwave from a single supernova explosion, or the intense radiation pressure from a cluster of young stars, could provide the final nudge needed to tip the entire cloud over the edge. This wouldn't be an external trigger, but an internal chain reaction, a stellar-scale domino effect where one wave of star birth violently compresses the surrounding gas, instantly triggering the next wave in a rapidly spreading frenzy of creation. The galaxy, in essence, would be spontaneously combusting from the inside out. An even more exotic proposal involves the mysterious hand of dark matter. While we often think of dark matter as a stable, passive scaffold, some theories suggest it could have a more dynamic role. If a small subhalo of dark matter, a clump of invisible mass, were to pass through the heart of the galaxy's gas disk, its gravitational influence could create a powerful ripple effect. As this unseen object plows through the gas, it would generate waves of density and compression in its wake, much like a boat moving through water. These waves could squeeze the gas clouds to the critical point of collapse, igniting star formation along a precise path without any visible cause. It would be a ghostly perturbation, an ignition source we cannot see, leaving behind only the brilliant firestorm as evidence of its passage. This burstiness, this ability to ignite with such violence in perfect peace, reveals that our understanding of star formation is still missing key chapters. It shows that the potential for cosmic fireworks is baked into the very fabric of a galaxy, waiting for the right internal cue to set it off, proving that even in the deepest solitude, a galaxy can hold the seeds of its own brilliant transformation. While we often picture galaxies as vast collections of stars, gas, and dark matter held together by gravity, there exists another, far more subtle force weaving through the cosmic fabric, one that is invisible to our eyes but whose influence can be profound. This is the force of magnetism, and in some galaxies, it behaves in ways that defy our expectations, creating patterns and exerting influences that our models simply cannot explain. Imagine the magnetic field of a galaxy not as a simple, orderly dipole like a bar magnet, but as a complex, tangled web of lines of force, sometimes stretching for tens of thousands of light years far beyond the galaxy's visible edge, orchestrating the flow of gas and the birth of stars from the shadows. This isn't science fiction. It's the reality observed in galaxies like the beautiful NGC 4631, also known as the Whale Galaxy, where radio telescope observations have revealed a magnificent and baffling magnetic halo. Seen in visible light, NGC 4631 is a classic edge-on spiral galaxy, a streaky disk of stars silhouetted against the blackness of space. But when we tune our instruments to perceive its magnetic personality, a stunning and entirely different structure emerges. Vast loops and filaments of polarized radio emission arc high above and below its galactic plane, tracing the lines of a magnetic field that is both incredibly ordered and immensely extended. These fields aren't confined to the dense regions of star formation. They soar into the galactic halo, a realm where we expected magnetism to be weak, disordered, or non-existent. The sheer scale and coherence of these magnetic structures present a direct challenge to our primary theory for how galaxies get their magnetic fields in the first place, the dynamo theory. This model suggests that galactic magnetic fields are self-sustaining engines, generated and amplified by the churning motion of ionized gas within the galactic disk. The rotational energy of the galaxy is converted into magnetic energy, a process that should, in principle, create fields that are strongest in the disk and fade quickly with height. The magnificent magnetic halos we see tell a different story, one where the fields are not only present but are highly organized in these remote regions, forcing us to ask how energy is being transported so efficiently from the turbulent disk into the calm halo. This disconnect between prediction and observation has led experts to propose some truly fascinating origins for these cosmic force twists. One compelling idea reaches back to the very beginning of everything: primordial magnetic fields. This theory suggests that these powerful fields are not made by the galaxy at all, but are instead ancient relics, fossils from the universe's explosive birth. In the intense energy of the Big Bang and the subsequent inflationary period, the cosmos may have seeded itself with a faint, all-pervading magnetic field. As matter collapsed to form galaxies, these primordial field lines would have been dragged along, compressed and amplified, becoming the strong, large-scale fields we detect today. They would be a fundamental part of the galaxy's foundation, not a later addition. The other leading theory sticks with the dynamo model but pushes it to its limits. Perhaps what we're witnessing is the work of a galactic scale wind. Intense star formation and supernova explosions in the disk could be driving a fountain of hot, ionized gas that erupts vertically out of the galaxy. As this gas surges into the halo, it could be dragging the magnetic field lines with it, stretching them and organizing them into the colossal loops we observe. In this scenario, the magnetic field is like smoke caught in the updraft of a colossal fire, revealing the invisible pathways of energy that flow out of a galaxy's bustling disk. The true significance of these magnetic anomalies lies not just in their origin, but in their power to shape galactic destiny. A magnetic field is not a passive ornament, it is an active participant in the life of a galaxy. These vast, ordered fields can influence the collapse of giant molecular clouds, either providing additional support against gravity to slow star formation, or acting as conduits that channel material inward to accelerate it. They can confine cosmic rays, the high-energy particles accelerated by supernova, preventing them from escaping and thus building up a pressure that can drive winds or even trigger further star formation. In the halos of galaxies, magnetic fields can provide a scaffolding that helps hold hot gas in place, preventing it from flying off into intergalactic space and thus preserving a reservoir of future star-forming fuel. The peculiar magnetic fields of galaxies like NGC 4631 are therefore more than just a curiosity. They are a crucial piece of the puzzle of galactic evolution, a hidden variable that we are only just beginning to appreciate, adding a layer of beautiful complexity to our understanding of how galaxies live and breathe. While our eyes are naturally drawn to the brilliant cores and sweeping arms of galaxies, the true story of their structure is often written in far more subtle ink, in the gradual, almost imperceptible fade of their light from center to edge. For generations, astronomers have used elegant mathematical formulas to describe this fade, believing they had captured the universal language of galactic architecture. The de Vaucouleurs law for the bulges of elliptical galaxies and the simple exponential decline for the disks of spirals became these universal rules, a photometric signature that every galaxy was expected to follow. These profiles weren't just arbitrary curves. They were the direct predicted outcome of the violent, chaotic process of hierarchical formation through mergers, a statistical endpoint that all galaxies should eventually settle into. To find a galaxy that brazenly ignores these rules, whose light tells a story that doesn't fit the standard plot, is to discover a relic of a different history entirely, a cosmic rebel that refused to conform. This is the realm of galaxies with unusual surface brightness profiles, and they present a challenge not with a shout but with a whisper. The most profound of these rebels are the low surface brightness galaxies, but their mystery isn't just that they are faint. It's in the specific, often bizarre way their light is distributed. Some exhibit a core that is far too large and diffuse for their mass, a vast, shallow sea of stars with no concentrated center. Others have extended outskirts, enormous, faint halos of starlight that stretch far beyond where any model says the galaxy should end, as if the galaxy is surrounded by a ghostly echo of itself. Then there are the galaxies with completely irregular light patterns, asymmetric dips and plateaus, sudden cliffs in brightness, or even central depressions that make them look like cosmic donuts. These aren't mere imperfections, they are glaring signatures that the standard playbook of mergers and violent relaxation simply did not apply here. The smooth, predictable light curves we take for granted are the hallmark of a system that has been thoroughly mixed and shaken by gravitational interactions. A galaxy that lacks this smoothness is therefore a galaxy that has lived a uniquely quiet and isolated life, a fossil preserved from a time before the cosmic dance began. Unraveling the meaning behind these anomalous light patterns requires the precise art of photometry, the careful measurement of starlight. When researchers like Stacy McGaw and others meticulously map the light in these systems, they are essentially reading a history book written in photons. A strangely extended outer halo, for instance, can be the unmistakable signature of a very ancient and very minor merger, the faint, dissolving corpse of a small galaxy that was cannibalized billions of years ago, its stars slowly smearing out into a vast cloud. A large, fluffy core, on the other hand, might point to a formation history almost entirely devoid of major mergers. Without the gravitational violence of repeated collisions to drive stars into a dense center, the galaxy would have formed puffed up from the start, its stars never experiencing the compressive forces needed to create a sharp, bright nucleus. In this case, the unusual light profile is a direct indicator of a profoundly peaceful past, but the plot thickens when we consider the invisible hand guiding it all, dark matter. The distribution of light in a galaxy is fundamentally a map of where its stars have been able to congregate, and that congregation is dictated by the shape of the gravitational well carved out by dark matter. A standard, dense dark matter halo creates a deep, narrow potential well, pulling stars inward to form a classic, bright core with a steep light decline. However, if the dark matter halo is instead unusually large and diffuse with a gentle core rather than a steep cusp in its center, the gravitational well will be wide and shallow. Stars forming in this placid gravitational basin would naturally arrange themselves into a much more spread-out configuration, resulting in the very low surface brightness profiles we observe. Therefore, a galaxy's strange light can be a direct window into the bizarre and varied nature of dark matter itself, suggesting that the invisible scaffolding of the universe comes in a much wider array of shapes and sizes than our simulations have yet predicted. This photometric puzzle ultimately reveals that there is no single path to building a galaxy. Each unique pattern of starlight is a lasting monument to its own distinct journey through cosmic time. After exploring the silent, magnetic architectures that shape galaxies from within, we now turn our attention to the dynamic and transient structures that flow through the cosmic environment like great oceanic currents. Envision vast, amorphous clouds of primordial gas, some containing more mass than 1 million suns, hurtling through the halos of galaxies at speeds of hundreds of kilometers per second. These are not the gentle, orderly flows predicted by simple models. They are high-velocity clouds, and their origin story is one of the most persistent and debated mysteries in modern astrophysics. They represent the vital, yet poorly understood, circulatory system of a galaxy, the constant inflow of fresh fuel and outflow of processed material that governs its growth, evolution, and ultimate fate. For our own Milky Way, these clouds appear as faint, shifting patches in radio telescopes, mapping the 21-centimeter emission of neutral hydrogen, tracing a complex and chaotic web of motion high above the serene disk of stars we call home. The central puzzle of these clouds lies in the conflicting stories told by their speed and their composition. If these were simply intergalactic gas clouds, pristine remnants from the formation of the cosmic web, now falling into the Milky Way for the first time, we would expect them to be made of almost pure hydrogen and helium, devoid of the heavier elements forged in stellar furnaces. Yet, spectroscopic analysis often reveals a surprising truth. Many of these clouds possess small but significant amounts of metals like oxygen, silicon, and iron. This chemical fingerprint is a telltale sign of enrichment, meaning this gas has already been inside a galaxy, touched by the life and death of stars, and then ejected back out into the halo. This immediately rules out a simple origin as virgin intergalactic material and points toward a galactic recycling process, but the exact mechanism remains hotly contested. Researchers have proposed three primary theories, each with its own compelling evidence and nagging inconsistencies. The first theory frames these clouds as tidal debris, the cosmic aftermath of a gravitational struggle. When a small dwarf galaxy or a globular cluster ventures too close to a massive spiral like the Milky Way, the immense tidal forces can shred it apart, pulling long, faint streams of stars and gas from its body. These streams, stretching across thousands of light years, could well include the high-velocity clouds we observe. The metallicities would match, as the material came from an already evolved system, and the motions could be explained by the chaotic dynamics of the disruption. However, connecting specific clouds to specific tidal events has proven difficult, and many clouds lack the clear kinematic association with known satellite galaxies or streams. The second theory paints a more self-contained picture, the galactic fountain model. In this scenario, the engine of expulsion is the galaxy itself. In regions of intense star formation, the combined effect of stellar winds and supernova explosions acts like a colossal pressure cooker, violently heating the surrounding gas and blasting it out of the galactic disk in brilliant hot bubbles. This material, now superheated to millions of degrees, surges high into the halo. Over millions of years, it gradually cools and condenses, forming dense clouds of neutral hydrogen that then rain back down onto the disk under the pull of gravity, completing the cycle. This elegant model explains the metallicities perfectly, as the gas is directly from the galaxy's star-forming regions. The challenge lies in the kinematics. While some clouds do show evidence of this fountain flow, many others have velocities and trajectories that are difficult to reconcile with a simple ballistic fountain originating from the disk. The third, and perhaps most profound, possibility is that these clouds are true intergalactic interlopers, but not pristine ones. They could be fragments of the vast, warm-hot intergalactic medium, the diffuse plasma that fills the space between galaxies in the cosmic web. This material could have been enriched by the galactic winds of entire populations of galaxies billions of years ago, acquiring a low level of metals before being accreted by the Milky Way. Alternatively, they could be the shredded remains of an ancient, long-forgotten galaxy that was completely torn apart in the distant past, its gas now swirling around our halo as a ghostly reminder. This would explain the odd motions and the slight metallicities, but it requires our galaxy to be actively accreting sizable lumps of pre-enriched gas from its environment, a process that is difficult to observe directly. The implications of this gaseous enigma extend far beyond mere classification. They strike at the heart of the galactic baryon cycle. galaxies need a continuous supply of fresh, cold gas to form new stars. If the primary source of this gas is the infall of high-velocity clouds, then understanding their origin is key to understanding the lifeblood of a galaxy. Furthermore, the outflows driven by supernova are a critical form of feedback, regulating star formation by ejecting gas and metals into the halo and beyond, thereby polluting the intergalactic medium and influencing the evolution of future generations of galaxies. The high-velocity clouds could be the crucial link in this cycle, the visible manifestation of this great exchange of matter. Their mysterious motions and compositions are not just a curious detail. They are a direct window into the most dynamic and ongoing processes of galactic evolution, a real-time snapshot of a galaxy breathing, feeding, and recycling the very elements of life on a cosmic scale. Now we arrive at one of the most conceptually challenging and controversial puzzles in all of astronomy, one that strikes directly at the tools we use to map the cosmos itself. For over a century, the redshift of a galaxy has been our primary ruler for measuring the vast distances of the universe. This is the cornerstone of modern cosmology, the observation that the light from distant galaxies is stretched or shifted toward the red end of the spectrum, and that this shift is proportional to their distance from us due to the expansion of the universe. It's a beautifully simple and powerful idea codified in Hubble's law that has allowed us to construct a three-dimensional map of the cosmos and even to understand its age and ultimate fate. The redshift is our guide, our cosmic GPS, and we trust it implicitly. But what happens when this trusted guide appears to give us a reading that defies all other visual evidence, suggesting that two galaxies that are clearly interacting, that are physically linked by bridges of gas and stars, are actually separated by billions of light years? This is the mind-bending anomaly of discordant redshifts, and it forces us into a terrifyingly exciting dilemma. Do we dismiss our eyes, or do we question our most fundamental ruler? The most famous and intensely studied case is that of the spiral galaxy NGC 7603 and its peculiar companion. In a stunning deep image photograph, NGC 7603 is seen with a smaller, oddly shaped galaxy seemingly attached to one of its spiral arms. More astonishingly, a faint but definite filament of luminous gas can be seen physically connecting the two, a cosmic umbilical cord that strongly suggests they are gravitationally bound and interacting. This visual evidence is compelling. It screams that these two galaxies are neighbors, likely in the process of a slow-motion dance that will eventually end in a merger. However, when we point our spectrographs at them, the story completely unravels. The redshift of the larger NGC 7603 places it at a distance of about 120 million light-years from Earth. But the redshift of the smaller, attached companion suggests a distance of nearly 1.5 billion light-years, over 10 times farther away. According to the standard cosmological interpretation of redshift, these two objects cannot possibly be near each other. The smaller galaxy should be far in the background, and the luminous filament connecting them must be a mere trick of perspective, a chance alignment. Yet the connection looks anything but chance. The filament is not a straight line. It has structure, it curves, it looks like a tidal tail pulled out during a gravitational interaction. Our two most trusted tools, the camera and the spectrograph, are giving us completely contradictory versions of reality. This paradox has, understandably, sparked fierce debate and a range of exotic explanations that venture to the very frontiers of physics. The most conservative explanation, and the one most astronomers lean towards, is that we are being fooled by a projection effect. Perhaps the smaller galaxy is indeed a distant background object, and the faint filament is not a physical bridge but an unrelated, faint dwarf galaxy or a jet of ejected material from NGC 7603 itself that just happens to line up perfectly with the background object. It would be an incredible cosmic coincidence, but the universe is vast, and such coincidences, however unlikely, do occur. The human brain is also notoriously good at finding patterns, even where none exist, a phenomenon known as pareidolia. Experts rightly caution that we must first exhaust all possible mundane explanations before invoking new physics. But if we take the connection at face value, we are forced to consider possibilities that would fundamentally reshape our understanding of the universe. One radical proposal is that of non-cosmological redshifts. This idea suggests that a galaxy's redshift might not be entirely due to the expansion of the universe. Perhaps a significant portion of it could be intrinsic, generated by some unknown physical process within the galaxy itself that imprints a redshift on its light as it escapes. If a galaxy could be born with a high intrinsic redshift, it would masquerade as being much farther away than it truly is. This would mean our entire cosmic distance ladder and the three-dimensional map of the universe we've built with it could be profoundly flawed in places. Another, even more speculative idea involves exotic physics related to light itself. Could the photons of light be losing energy over their immense journey through space in a way we don't yet understand, perhaps through a subtle interaction with the intergalactic medium or even with dark energy, causing a redshift that isn't purely velocity-based? The case of NGC 7603 is not isolated. Other puzzling associations have been found, such as the galaxies around the quasar Markarian 205 and the galaxy NGC 4319, which also appear connected yet have conflicting redshifts. Each new case adds weight to the mystery, suggesting that either we are witnessing a series of statistically near impossible alignments, or there is a lingering flaw in our interpretation of the cosmos's most important signal. This association challenge is more than a curious academic debate. It is a direct stress test for the foundation of observational cosmology. It forces us to be humble, to acknowledge that our grasp on the universe's scale and behavior might still have critical blind spots. Whether the ultimate answer lies in better observations that resolve the filaments or in a revolutionary new theory of light and gravity, these anomalous pairs stand as permanent reminders that our cosmic map, for all its detail, may still contain regions marked "Here be dragons." But if the serene counter-rotation of stars presents a puzzle of internal conflict and the anomalous redshift challenge our cosmic maps, then the next anomaly reveals a gravitational tango of almost unimaginable power and scale, happening in the very hearts of galactic giants. We've journeyed through the aftermath of mergers, seeing the distorted shapes and tidal tails they leave behind. The logical next step in that violent cosmic dance is the fate of the central engines themselves, the supermassive black holes. Theory tells us that when two galaxies collide and merge, their central black holes, each weighing millions or even billions of solar masses, should eventually find each other. Drawn together by gravity, they are predicted to sink to the center of the new, combined galaxy and begin a slow, orbital waltz, becoming a supermassive black hole binary, a dual-engine heart pumping unimaginable gravitational energy. This is a cornerstone prediction of our hierarchical model of galaxy formation. The universe should be filled with these circling titans, yet finding them has proven to be one of the most frustrating and elusive quests in modern astrophysics. The challenge of detection is immense. We cannot see the black holes themselves, only the inferno of light produced by the superheated gas and dust swirling around them in an accretion disk. When two black holes are far apart in their orbit, They may each have their own distinct disk, but from our distant vantage point millions of light years away, their light blends into a single, unresolved point. It's like trying to distinguish two fireflies circling each other from a mile away. They appear as one unchanging speck of light. The key to unlocking their secret lies in their motion. As they orbit, their gravitational influence can periodically disturb their own accretion disks, or the Doppler shift of light from gas closely bound to one black hole can reveal its changing velocity. The most compelling evidence comes from systems that show predictable, periodic flickering in their brightness, a telltale signature of an orbital clockwork ticking away at the core. A prime candidate is the Blazar OJ287, located about 3.5 billion light-years away. This galaxy's core is a beacon of intense, variable light, and for over a century, astronomers have been meticulously recording its outburst. They discovered a fascinating pattern, major flares occurring roughly every 12 years, with a pair of outbursts happening within about a year of each other in each cycle. The leading explanation for this precise celestial clock is the presence of a supermassive black hole binary. In this model, the smaller black hole, weighing about 150 million solar masses, orbits a truly monstrous primary black hole over 18 billion times the mass of our Sun. The smaller black hole's orbit is tilted, so it punches through the primary's gargantuan accretion disk twice per orbit. Each plunge through the disk unleashes a titanic shockwave, heating the gas to incredible temperatures and producing the brilliant double-peaked flares we observe. The timing is so precise that general relativistic effects, which cause the orbit itself to precess, must be taken into account to predict the next flare. It's a stunning confirmation of Einstein's theory and a powerful, albeit indirect, case for a binary system. Yet, for every OJ287, there are thousands of merged galaxies where we see no such signal. This is the heart of the puzzle, their apparent elusiveness. Why aren't they everywhere we look? The answer seems to lie in the final parsec problem. As two black holes spiral toward each other, they initially lose energy efficiently by slingshotting stars that pass nearby. But as they get within about 1 parsec, just over 3 light-years, of each other, they risk entering a barren region. They may have effectively cleared out all the nearby stars that could rob them of orbital energy. Without this dynamical friction, their inward spiral could stall, stranding them in a stable, billion-year orbit without ever getting close enough for gravitational wave emission to finally bring them together. They become stuck, a long-lived binary system that is incredibly difficult to detect unless, like OJ287, it has a specific mechanism for creating bright, periodic flares. This is where insights from the new field of gravitational wave astronomy become crucial. While we have not yet detected the low-frequency gravitational waves from supermassive binaries with our current observatories, their expected collective hum is a primary target for upcoming space-based detectors like the Laser Interferometer Space Antenna, or LISA. The prevalence and orbital periods of these binaries will write a definitive history of galaxy mergers throughout cosmic time. Furthermore, the complex dynamics of a binary system can have profound feedback effects on its host galaxy. The gravitational kicks from a circling binary can fling stars out into the halo, alter the structure of the central stellar cluster, and disrupt the inner accretion disk, potentially starving the black holes themselves of fuel and affecting the entire galaxy's growth and activity. The difficulty in finding them isn't just an observational challenge. It's a direct window into the complex and messy physics of the final stages of a galactic merger, a slow-motion dance of darkness that dictates the ultimate fate of the universe's most powerful engines. While the grand spirals and brilliant starbursts of galaxies capture our immediate attention, The true architects of cosmic structure work in perfect darkness, hidden from view. We've come to accept the presence of dark matter halos as a fundamental truth, the invisible scaffolding that dictates the form and fate of every galaxy. Our cosmological models, primarily the lambda cold dark matter paradigm, make very specific predictions about what these halos should look like. They are expected to be abundant, with thousands of small subhalos swarming around every large galaxy like bees around a hive. And their density should follow a specific profile, rising steeply and sharply toward a dense, peaked center, a feature astronomers call a cusp. These are not arbitrary guesses. They are the direct outcomes of running our universe's known physics, including gravity and the properties of cold, slow-moving dark matter, through the most powerful supercomputer simulations we have. The virtual universes these simulations create are stunningly successful at reproducing the large-scale cosmic web of filaments and clusters. But when we zoom in to examine the dark matter halos of individual galaxies, especially the smaller, fainter ones, the model's predictions and our real-world observations begin to diverge in ways that are deeply troubling. This tension manifests in two of the most persistent and famous problems in modern cosmology, the missing satellites problem and the cusp core problem. Let's start with the missing satellites. Our simulations of a Milky Way-sized galaxy predict that its gravitational pull should have captured and retained hundreds, if not thousands, of small, dark matter subhalos. These subhalos should be massive enough to host their own small, faint dwarf satellite galaxies. Yet, when we actually count the number of satellite galaxies orbiting our own Milky Way, we only find about 60 that are confirmed. Now, it's possible that many of those predicted subhalos are simply too dark, containing no stars at all, which would make them invisible to our telescopes. But even when we account for that, the number of visible satellites still falls short of the simulation's predictions. It's as if the universe built an entire metropolis, but only ever bothered to light up a few dozen buildings, leaving the rest in complete darkness. This discrepancy suggests that something in our model is wrong, either about how easily gas collapses to form stars in these small halos, or about the very number and nature of the halos themselves. The second issue cuts even deeper, right to the heart of the halos themselves. The cusp core problem deals with the internal structure of these dark matter clumps. The simulations consistently tell us that dark matter halos should have a cuspy center, a region where the density of dark matter skyrockets dramatically as you approach the very middle. However, when astronomers study the motions of stars within real dwarf satellite galaxies, they can map out the gravitational field and infer the underlying dark matter distribution. In galaxy after galaxy, from the Fornax dwarf to the Sculptor dwarf, the data tells a different story. Instead of a steep, dense cusp, these galaxies seem to possess a core, a central region where the dark matter density is constant, flat, and much lower than predicted. It's the difference between a mountain with an impossibly sharp, Matterhorn-like peak and a gently rounded hill. This is not a minor accounting error, it's a fundamental architectural flaw. The dark matter in these real galaxies appears to have been somehow smoothed out, as if some force prevented it from collapsing into the dense, cuspy centers that the cold dark matter model demands. These are not abstract problems, they are direct, observational contradictions that have forced cosmologists to reconsider the very nature of dark matter. As one leading researcher put it, these anomalies are the most significant small-scale challenges facing the lambda CDM model. The solutions being proposed are nothing short of revolutionary. One compelling idea is that dark matter might not be cold after all, but warm. In this model, warm dark matter particles would be lighter and faster moving than their cold counterparts. This slight tweak has profound consequences. those faster-moving particles would have washed out the very smallest density fluctuations in the early universe, meaning fewer of the tiniest dark matter superhalos would ever form. This would neatly solve the missing satellites problem by reducing the number of predicted superhalos to a level much more in line with what we actually observe. Another fascinating proposal is that dark matter could have a way to interact with itself. In our standard model, dark matter particles are assumed to be collisionless. They pass right through each other and through normal matter like ghosts. But what if that's not entirely true? What if dark matter particles can occasionally bump into each other, exchanging energy and momentum? This self-interacting dark matter would behave less like an invisible gas and more like a subtle fluid. As a halo forms, these self-interactions would transfer heat from the hotter, denser outer regions into the cooler center, effectively puffing it up and eroding the sharp central cusp into a smooth, constant density core, exactly what we see in the data. It's a remarkably elegant solution that uses the particles' own interactions to solve the distribution problem they created. The ongoing investigation into these halo oddities is more than just technical model fitting. It is a direct assault on one of the greatest mysteries in science. The distribution of dark matter on the scale of individual galaxies is our most powerful probe of its fundamental properties. Is it cold, warm, or even something else entirely? Is it truly as inert as we think, or does it harbor a rich, hidden physics of its own? Every dwarf satellite galaxy we map, every rotation curve we measure, is another piece of evidence in this grand cosmic trial. The verdict will not only tell us what dark matter is made of, but will ultimately rewrite the story of how every structure in our universe, from the smallest dwarf to the largest cluster, came to be. After delving into the profound gravitational implications of misaligned dark matter halos, we now turn our gaze to a far more visible, yet equally puzzling cosmic irregularity. The simple, striking fact that some galaxies are just fundamentally lopsided. We often envision galaxies as perfect, balanced structures, majestic, symmetrical pinwheels or smooth, featureless ellipsoids. This expectation of order is rooted in the very physics that governs them. Gravity is a force that naturally works to smooth out irregularities, to pull matter into the most stable, lowest energy configuration, which is usually one of beautiful symmetry. So when we find a galaxy that brazenly flaunts its asymmetry, with a disk that is noticeably heavier on one side, spiral arms that are longer and more pronounced on a single flank, or a bright nucleus that sits conspicuously off-center, it's more than just a curiosity. It is a direct challenge, a cosmic imbalance that demands an explanation for why the universal tendency towards order has, in this specific case, spectacularly failed. The Grand Spiral Galaxy M101, also known as the Pinwheel Galaxy, is a textbook example of this persistent lopsidedness. From a distance, it appears as a classic face on spiral, a whirlpool of stars and gas. But a closer, quantitative look reveals that its disk is not uniform. The distribution of its neutral hydrogen gas is profoundly asymmetric, with one side of the galaxy extending significantly farther out than the other. This isn't a subtle effect, it's a clear and measurable imbalance in the galaxy's fundamental structure. The most common explanation for such a feature is a recent gravitational interaction. A close encounter with a neighboring galaxy can exert a powerful tidal force, pulling and stretching the disk, much like the Moon's gravity pulls on Earth's oceans to create tides. This could easily create a temporary, one-sided distortion. The problem with this neat solution for M101 is the apparent lack of a suitable culprit. There is no large, interacting galaxy nearby that could have recently caused such a dramatic and persistent distortion. the tidal trigger is absent, leaving the lopsidedness without a clear cause. This forces astronomers to consider more subtle and enduring mechanisms. One compelling theory is that of ongoing asymmetric gas accretion. Imagine a galaxy like M101 not as an isolated island, but as a dynamic structure that is still growing. Faint cold filaments of primordial hydrogen gas, remnants from the formation of the cosmic web, might still be flowing into it from a specific direction in space. If this cosmic rainfall is not even, if one side of the galaxy is receiving a steady trickle of fresh gas while the other side is not, it would naturally lead to an imbalance. The side receiving the influx would have more material to form stars, potentially creating a brighter, more extended disk on that flank. This would be a gentle, continuous process, a slow and persistent feeding that could maintain the lopsidedness over billions of years without the need for a violent, disruptive collision. Another fascinating possibility ventures into the realm of the invisible, suggesting that the asymmetry might not be in the stars and gas we see, but in the dark matter halo itself. Our models typically assume that these halos are smooth and symmetrical, but what if they are not? What if the dark matter distribution is itself lumpy or skewed? A lopsided gravitational potential generated by an asymmetrical dark matter halo would naturally tug on the visible disk, forcing the stars and gas to settle into an off-center, unbalanced configuration to match the invisible terrain. The galaxy's visible imbalance would simply be a reflection of an even deeper, hidden asymmetry in its dark foundation. This idea turns the problem on its head, suggesting that the answer lies not with the visible material, but with the mysterious, unseen 85% of the galaxy's mass. The most perplexing part of this mystery is not the origin of the lopsidedness, but its sheer longevity. Why don't these galaxies simply self-correct? Given enough time, shouldn't the relentless pull of gravity and the internal friction between stars eventually smooth out the asymmetry, allowing the galaxy to settle back into a stable, symmetrical shape? The fact that we see so many lopsided galaxies, with their distortions persisting for what must be many galactic rotation periods, indicates that these are not temporary states. They are stable configurations. This suggests that the forces creating the imbalance are not one-off events, but are persistent, ongoing influences. It could be that the same mechanism that caused the lopsidedness, be it the gentle rain of accretion or the pull of a skewed dark matter halo, is still actively at work, continuously counteracting gravity's smoothing effect. The galaxy exists in a state of balanced imbalance, a dynamic equilibrium where the distorting force and the restoring force of gravity have reached a strange, stable truce. This persistent external influence, whether from the cosmic web of gas or the hidden hand of dark matter, reveals that a galaxy's final form is not just the product of its initial conditions, but is constantly being shaped and reshaped by its ongoing dialogue with the invisible structures of the cosmos. While we often picture galaxies as island universes floating in the void, the truth is far more interconnected. Each galaxy, from the mightiest spiral to the faintest dwarf, is a single knot in a vast and magnificent cosmic tapestry. This is the cosmic web, the largest known structure in the universe, a spider's network of massive filaments, immense voids, and dense clusters that defines the distribution of all matter. For a long time, our models of galaxy evolution focused primarily on a galaxy's immediate neighborhood, its merger history, and the local density of its surroundings. But a deeper mystery is now coming into focus, one that ties a galaxy's fate directly to its address within this grand, large-scale architecture. The most revealing addresses aren't in the crowded cities of clusters or the empty deserts of voids, but along the bustling cosmic highways that connect them, the filaments themselves. Envision these filaments not as simple strings of pearls, but as dynamic rivers of dark matter and gas, flowing through the darkness and guiding the formation and evolution of the galaxies that form within them. When we look at the precise three-dimensional maps of the universe created by monumental surveys like the Sloan Digital Sky Survey, a clear pattern emerges. Galaxies that are embedded within these filaments, especially those at the intersections where multiple filaments meet on their way to a massive cluster, show distinct and enhanced properties. They often exhibit higher rates of star formation, their gas reservoirs seem richer, and their motions are more coherent, as if they are all flowing together along the same invisible current. This is a level of environmental influence that goes far beyond whether a galaxy has a close neighbor. It's about how the entire large-scale gravitational field of the filament is shaping its destiny from birth. Experts like cosmologist Noam Libeskind have been at the forefront of using sophisticated simulations to unravel this complex relationship. He describes the cosmic web not as a static backdrop, but as an active and dynamic player in the story of each galaxy. The filament acts as a cosmic conveyor belt, channeling vast quantities of pristine gas from the voids toward the hungry clusters. A galaxy situated along this belt finds itself in a privileged position, with a continuous supply of fresh fuel delivered right to its doorstep. This steady accretion can sustain star formation for much longer than in a galaxy isolated in a void, which must rely on its finite internal supply. Furthermore, the gravitational torque within the filament can gently spin up the gas, promoting the formation and stability of rotating disks, essentially setting the stage for a galaxy to become a grand spiral rather than a featureless elliptical. But the influence of the filament is even more nuanced than simply providing a bounty of gas. The specific geometry and density of the filament can dictate a galaxy's very motion and orientation. In a stunning correlation known as spin-filament alignment, studies have shown that the spin axes of spiral galaxies are not randomly oriented with respect to the filament they reside in. Instead, the disks of smaller galaxies tend to align their spin with the filament's direction, as if rolling along it like a tire on a road, while the most massive galaxies often orient their spins perpendicular to it. This is a direct signature of the tidal gravitational forces exerted by the entire large-scale structure, a force that can torque a galaxy into a specific alignment during its formation, leaving a permanent imprint billions of years later. The cosmic web doesn't just feed galaxies, it tells them which way to spin. This profound connectivity forces a major shift in our perspective. We can no longer view a galaxy as an isolated system whose fate is determined solely by local mergers. Its entire life cycle, its growth, its morphology, its star-forming efficiency, and even its final motion is deeply intertwined with its location on the cosmic web. A galaxy born in a dense filament is handed a script written by the gravitational forces of the entire universe, a script that directs it toward a different evolutionary path than a galaxy born in the profound isolation of a void. This reveals a universe of breathtaking order and interdependence, where the largest structures imaginable reach down with invisible hands to sculpt the smallest details of galactic existence, weaving every star and every nebula into the single, glorious structure of the cosmos. If the grand architecture of the cosmic web sets the stage for a galaxy's life, then its spin is the signature of its very first dance. We often take for granted that a galaxy will rotate, its stars and gas swirling in a graceful, balanced whirl that gives it structure and stability. This rotation isn't random. It's a fundamental birthright, a quantity of spin known as angular momentum that is imparted to a galaxy in its infancy and largely conserved throughout its life. The prevailing theory for how this happens, called tidal torque theory, is an elegant and intuitive idea. As a proto-galactic cloud collapses in the early universe, it doesn't do so in isolation. The gravitational tides from its nearest neighbors, the subtle tug of surrounding dark matter halos, act on it, setting it spinning. It's a cosmic version of twisting a doorknob. The initial torque determines the final rotation. This process should produce a relatively narrow, predictable range of galactic spins, a standard rotational velocity that correlates neatly with a galaxy's mass. But as with every rule in cosmology, the universe delights in creating spectacular exceptions. Scattered throughout the cosmos are galaxies that are either cosmic sluggards, rotating with a lethargy that defies their size, or hyperactive spinners, whirling at a pace that should tear them apart. These rotational outliers are more than just oddities. They are direct challenges to our understanding of the very first moments of galactic birth. Consider the case of a massive spiral galaxy that barely rotates at all. Its stars move with a strange, disordered randomness, more like the swarm of bees in an elliptical galaxy than the orderly, circular flow of a typical disk. Without significant rotation to provide centrifugal support against the pull of gravity, such a galaxy should, in theory, collapse inward upon itself. Yet it persists. On the opposite extreme, imagine a small, faint dwarf galaxy where the stars are hurtling around at breathtaking speeds, its rotation so frenetic that the galaxy should be flinging its outer stars into the void like a spinning ice skater launching a partner. These spin extremes are not just curiosities. They are profound anomalies that force us to ask what could possibly interfere with the fundamental process of angular momentum acquisition. The answer seems to lie in a galaxy's personal history of violence and feedback. For the sluggish rotators, the culprit is often a history of catastrophic mergers. While tidal torques provide the initial spin, a major galactic collision can effectively act as a cosmic brake. When two galaxies merge, their orbital angular momentum is converted into random internal motion, heating up the stellar population and erasing the ordered rotation of the original disks. The result is the puffed-up, slowly rotating or non-rotating ellipsoid of an elliptical galaxy. But some galaxies seem to have had their spin sapped without being completely destroyed, left in a strange, intermediate state that hints at a particularly violent or disruptive encounter that robbed them of their spin without fully scrambling their structure. For the hyperspinners, the explanation often points to a different kind of history, one of exceptional isolation and quiet feeding. A galaxy that forms in a particularly quiet region of the universe, far from the major tidal influences that normally set the spin, might collapse under its own gravity with its internal gas clouds conserving their own innate angular momentum. This can lead to a runaway effect where the galaxy spins up to an extreme degree. Alternatively, a galaxy might experience a very specific and narrow stream of cold gas accretion. If this gas flows in along a precise path that adds a tremendous amount of rotational energy, it could, over billions of years, act like a gentle hand on a spinning top, steadily accelerating the galaxy's rotation to anomalously high speeds. This is a form of spin-up that is far more gentle and precise than the violent, spin-destroying effects of a major merger. The most fascinating insights into these outliers come from detailed kinematic maps, charts of the motion of stars and gas within a galaxy. These maps can reveal the ghostly signatures of past events. A galaxy with unusually low spin might show faint tidal streams or a disturbed core, the lasting scars of a merger that halted its rotation. A galaxy with extreme spin might show a peculiarly settled and thin disk, indicating a long, quiet history without disruption, allowing its rotation to amplify and refine itself over eons. What sets a galaxy's spin, therefore, is not a single event at birth. but the totality of its life story, the pushes and pulls, the mergers and accretions, the violent shocks and the serene flows of gas that either preserve, enhance, or diminish that initial rotational kick. This rotational rarity does more than just catalog unusual galaxies. It provides a critical stress test for our models of feedback and accretion, revealing the delicate and complex balance of forces that determine whether a galaxy will become a stately whirlpool, a chaotic swarm, or something entirely unique in between. While we often classify galaxies by their shape or size, one of the most immediate and visceral ways we perceive them is through their color. A galaxy's hue is its visual autobiography, a direct record of the stars that live within it. Brilliant blue tones shout the presence of massive, young, hot stars, burning fiercely and dying young. Soothing red and golden glows whisper of ancient stellar populations, cooler and quieter, steadily burning through their fuel over billions of years. This color coding is a fundamental language of astronomy, allowing us to read a galaxy's star formation history at a glance. We've built sophisticated synthetic models that predict, with remarkable accuracy, what color a galaxy should be based on its mass, its type, and its chemical composition. It's a system that works until it doesn't, because scattered throughout the cosmos are chromatic rebels galaxies whose colors tell a story that simply doesn't match the book they're supposed to be in. These are the galaxies with anomalous color distributions, and they force us to question not just our reading of their history, but the very rules of stellar life and death. Consider the case of a massive elliptical galaxy. These are meant to be the retirement communities of the universe, composed almost entirely of old, red stars. Their star-forming days are long over, and their color should be a uniform, rusty gold from core to edge. But what do we make of an elliptical that shows a startlingly blue core, a vibrant splash of youthfulness at its heart where only old age should reside? Conversely, imagine a spiral galaxy like our own Milky Way, a place where active star formation in its spiral arms should paint them a luminous blue. Now picture finding a spiral whose arms are an unexpectedly dusty red, not from a lack of stars, but from a filter we didn't expect. These chromatic curiosities are more than just a misfit in a catalog. They are glaring signals that a galaxy has either experienced a recent, secret burst of activity, or that something is fundamentally altering our perception of its stellar population. Unraveling this puzzle requires the precise science of photometry, the meticulous measurement of starlight across different wavelengths. When astronomers conduct these detailed analyses, they are often comparing the real galaxy to a synthetic stellar population model, a kind of theoretical recipe that combines different types of stars to produce a certain color. As one researcher noted, when the real galaxy's colors deviate significantly from the model's prediction, it's a sure sign that the recipe is wrong. The ingredients themselves might be off. One radical possibility is that the initial mass function, the rule that dictates how many stars of each size are born when a gas cloud collapses, is not the universal constant we believe it to be. We assume that a giant molecular cloud will always produce a certain distribution, countless small, dim red dwarf stars for every massive, brilliant blue giant. But what if, in certain extreme environments, that rule changes? In a galaxy with an unusually high pressure or a bizarre chemical makeup, the cloud might preferentially form only high-mass stars or only low-mass stars, completely skewing the galaxy's color away from the expected norm. A galaxy that formed nothing but blue giants would appear shockingly, transiently blue before exploding into oblivion. A galaxy that somehow only made red dwarfs would be mysteriously and permanently red. Another powerful explanation lies not in the stars themselves, but in what lies between them: cosmic dust, tiny grains of silicon and carbon forged in the atmospheres of old stars and scattered by supernova acts as a powerful filter. This dust is exceptionally efficient at scattering blue light, the same phenomenon that makes our own sky appear blue. In a galaxy with an unexpected distribution of dust, perhaps vast, opaque clouds concentrated in its disk rather than spread evenly, the light from its brilliant blue stars could be being absorbed or redirected, making the entire galaxy appear much redder than it truly is. We would be seeing a galaxy through a cosmic haze, its true vibrant colors muted and disguised. Alternatively, the anomalous color could be the result of an external influence. A galaxy might be being polluted by the ejected material from a nearby neighbor, its gas suddenly enriched with metals that affect how new stars form and what color they shine. Or it could be the victim of a phenomenon called galactic harassment, where the gentle but persistent tidal forces from passing galaxies stir up its gas, triggering a small, localized burst of star formation that paints a single region a brilliant blue against a sea of red. This chromatic challenge ultimately forces us to look at galaxies not as static paintings, but as dynamic systems with complex and sometimes hidden histories. A color anomaly is a clue, a piece of evidence in a cosmic investigation. It can point to a recent, hidden merger that injected a rush of fresh gas and sparked a firestorm of new stars where there should be none. It can reveal the presence of immense, unseen dust lanes that are secretly shaping our view. Or, in its most profound interpretation, it could be hinting that the very rules of star formation are not as universal as we thought, that the initial mass function can vary from place to place across the cosmos. The color of a galaxy is the first thing we see, but for these anomalous systems, it is the beginning of a much deeper mystery, one that connects the grand scale of galactic evolution to the fundamental physics that governs the birth of every single star. Imagine for a moment the most powerful flash in the universe, a blast of radio energy so intense that it can outshine 500 million suns, yet it lasts for less than 1,000th of a second. These are fast radio bursts, some of the most enigmatic signals we've ever detected, appearing seemingly at random from the depths of space and then vanishing without a trace. For years, they were cosmic ghosts, one-off events that defied explanation. But then came a revolution, the discovery of a repeater, a single source now known as FRB 121102 that didn't just flash once, but again and again, sending out powerful bursts on a schedule only it understood. This repetition was the key that finally allowed astronomers to do something extraordinary, to track the signal back to its home galaxy, and what they found there was not at all what anyone expected. This incredibly powerful, energetic phenomenon wasn't coming from a massive elliptical galaxy or the busy center of a cluster. It was originating from a small, faint, unassuming dwarf galaxy over 3 billion light-years away, a place that seemed utterly incapable of hosting such a cosmic powerhouse. This is the profound mystery of galaxies with mysterious fast radio burst associations. It's a puzzle that operates on two levels simultaneously. What is creating these incredible bursts, and why are they consistently found in such peculiar galactic environments? The host galaxy of FRB 121102 and many other repeating FRBs discovered since share a family resemblance that is deeply telling. They are often small, dwarf galaxies, but they are far from quiet. They are stellar nurseries humming with intense star formation, churning out new suns at a rate that belies their modest size. Furthermore, they are cosmic teenagers in terms of their chemical maturity. They possess surprisingly low metallicities, meaning they are lacking in the heavy elements that are forged in the lives and deaths of generations of stars. This combination of traits, small size, frantic star birth, and primordial chemistry, paints a very specific portrait of a young, chaotic, and rather primitive galaxy. It's a place that feels more like the early universe, a turbulent and unsettled environment where the rules might be very different. The fact that the most energetic transient phenomena we know of prefer these specific conditions is a massive clue, one that is forcing a complete rethink of what powers them. The leading theories for what causes an FRB are already exotic, involving some of the most extreme objects in physics. The prime suspect has long been a magnetar, a type of neutron star with a magnetic field so powerful it could strip the information from a credit card from halfway across the solar system. The idea is that a starquake on the surface of such an object, a sudden cracking of its incredibly dense crust, could release a titanic shockwave that unleashes the radio burst. Another theory points to an actively accreting black hole, with instabilities in its surrounding disk of material launching powerful jets that could generate the signal. But the galactic homes of these FRBs are challenging both ideas. The low metallicity of these dwarf galaxies suggests their stars are made from pristine, primordial gas. When such stars die, they are predicted to collapse differently, potentially creating magnetars with even more intense magnetic fields, or perhaps forming black holes through direct collapse, skipping the supernova stage entirely. The environment is perfect for creating the most extreme versions of these already extreme objects. The high rate of star formation ensures there's a constant supply of new neutron stars and black holes, while the lack of heavy elements might allow them to form in ways we rarely see in our more evolved, metal-rich cosmic neighborhood. This transient link is so fascinating because it probes the delicate intersection between stellar-scale physics and galactic-scale evolution. It asks a profound question: does the large-scale environment of an entire galaxy, its mass, its chemistry, its star-forming intensity, dictate the types of stellar corpses it can produce? The answer appears to be a resounding yes. The conditions in these faint, bustling dwarf galaxies seem to be the perfect cosmic crucible for forging the specific kind of stellar remnant that can power an FRB. It's a stunning connection that turns these faint, distant galaxies into invaluable laboratories. We cannot create a magnetar on Earth, and we cannot watch a black hole form up close. But by studying the galactic homes of FRBs, we can reverse engineer the recipe. We can start to understand the specific ingredients, the gas purity, the stellar density, the violence of star birth that are required to cook up such a phenomenal event. Each repeating burst is like a flare sent up from this laboratory, giving us another precious data point. The mystery of the fast radio burst is no longer just about the burst itself. It is about the entire galactic ecosystem that makes it possible, a reminder that the smallest, most fleeting events in the cosmos can be deeply tied to the largest and most enduring structures. For centuries, physics has operated in two distinct realms: the very large, governed by the smooth, geometric curves of Einstein's general relativity, and the very small, ruled by the fuzzy, probabilistic laws of quantum mechanics. These two pillars of modern science are spectacularly successful in their own domains, but they are fundamentally, stubbornly incompatible. Unifying them into a single theory of quantum gravity is perhaps the greatest unsolved problem in all of physics. The search for this holy grail has largely been the domain of particle accelerators and mathematical theory, conducted at energy scales and distances we can scarcely imagine. But what if the key to unlocking this deepest of cosmic secrets isn't hidden in a subatomic particle smasher, but is written large across the sky, encoded in the very structures of galaxies themselves? This is the breathtakingly speculative frontier we now approach, where the anomalies of galactic behavior become potential tests for the most profound ideas about the nature of reality. The connection seems absurd at first glance. How could a galaxy, an object comprising hundreds of billions of stars spanning over 100,000 light-years, possibly be sensitive to the Planck scale, the unimaginably tiny distance of 10 to the minus 35 meters, where the fabric of spacetime itself is thought to become granular and foamy? The answer may lie not in the galaxies themselves, but in the subtle, cumulative effects that a granular spacetime might have on things like the propagation of light and the precise nature of gravity over these immense cosmic distances. For instance, one of the most persistent anomalies we've explored is the behavior of galactic rotation curves. The standard solution is dark matter, but some theorists working on alternatives like modified Newtonian dynamics have wondered if a slight modification of gravity on certain scales could do the job. This opens a door. Could that modification be a low-energy signature of a much deeper quantum gravity effect? If spacetime at a fundamental level has a discrete, pixelated structure, it might not behave with perfect smoothness. Over the vast distances within a galaxy, these tiny imperfections could, in theory, add up to a measurable deviation from the predictions of pure general relativity, manifesting as the need for extra mass or a change in the gravitational force. This line of thinking extends to other phenomena like gravitational lensing. When the gravity of a galaxy cluster bends the light from a more distant object, it creates arcs and rings that act as a precise scale for the cluster's total mass. Any discrepancy between the mass calculated from lensing and the mass calculated from the motions of stars could be a clue. Some highly speculative proposals within theories like loop quantum gravity or string theory suggest that quantum fluctuations of spacetime might affect how light travels through it, potentially altering the lensing signal in a subtle but detectable way. It's a long shot, but the potential payoff is so enormous that it fuels the imagination. Could a detailed statistical analysis of thousands of lensing systems eventually reveal a pattern that only a specific theory of quantum gravity can explain? Of course, the vast majority of astrophysicists urge extreme caution. It is all too easy to label something we don't understand, like dark matter or dark energy, as quantum gravity and feel like we've explained it. This is a classic case of invoking magic when our current models fall short. Experts rightly point out that exotic but conventional astrophysics is almost always a more likely explanation than rewriting the fundamental laws of the universe. The history of science is littered with failed theories that try to explain away observational anomalies with new physics, only to have them later resolved within the existing framework. The burden of proof for someone claiming evidence of quantum gravity in a galactic rotation curve is astronomically high. They must first rule out every possible systematic error, every subtle baryonic effect, and every conceivable property of dark matter before their proposal can be taken seriously. Yet, despite these justified cautions, this speculative pursuit is vital. It represents a shift in how we might finally test these incredibly abstract theories. For decades, ideas like string theory have been criticized for being beautiful mathematics that is fundamentally untestable, forever beyond the reach of any conceivable experiment. If, however, their effects can indeed imprint themselves on the largest structures in the universe, then our telescopes and galaxy surveys become our microscopes. Each anomalous galaxy, each strange lensing measurement, becomes a data point that could, in principle, constrain the parameter space of these theories. It encourages a beautiful synergy between the cosmologist mapping the large-scale structure of the universe and the theoretical physicist working on 10-dimensional manifolds. They might be studying the same thing from opposite ends of the cosmic spectrum, This frontier doesn't promise easy answers, but it invites the boldest of theoretical leaps, challenging us to see the cosmos not just as a collection of objects, but as the ultimate laboratory for probing the very fabric of space-time. For over a century, the towering edifice of Einstein's general relativity has reigned supreme, its elegant equations describing gravity not as a force, but as the curvature of space-time itself, a geometric dance of mass and energy that has predicted everything from the bending of starlight to the existence of black holes with breathtaking accuracy. It is the foundation of modern cosmology, the framework upon which we've built our entire understanding of the universe's history and fate. Yet, this magnificent structure is built upon a fundamental assumption that the laws of gravity as defined by Einstein and Newton are universal, unchanging, and absolute at all scales. But what if, when we peer into the deepest, darkest reaches of galactic space, we are seeing the first faint cracks in that foundation? What if the very force that holds the cosmos together behaves differently in the realms of extreme faintness and low acceleration? This is the radical and compelling proposition of modified Newtonian dynamics, or MUND, a theory that dares to suggest that we may not need invisible legions of dark matter to explain the universe. We may just need to rewrite the rules of gravity itself. The central pillar of MUND is both simple and revolutionary. It proposes that Newton's second law of motion, F equals ma, undergoes a subtle but crucial modification at extremely low accelerations, specifically below a critical threshold of about 1/10 of a meter per second squared. In the everyday world and in the strong gravitational fields of our solar system, where accelerations are high, Newton and Einstein's laws hold perfectly. But in the outer, sparse regions of galaxies, where the gravitational pull from the visible matter becomes almost imperceptibly weak, MUND suggests that the force of gravity begins to decline more slowly than the inverse square law predicts. This single, elegant tweak has a stunning consequence. It naturally produces the flat rotation curves observed in spiral galaxies without requiring any additional, unseen mass. The gravity itself becomes stronger than expected in these faint outskirts, perfectly mimicking the gravitational effect of a dark matter halo, but without the need for the halo itself. It's a breathtakingly economical idea, solving the mystery not by inventing a new, invisible substance, but by modifying the behavior of the one force we thought we knew. The most powerful evidence for MUND comes from its stunning predictive power, particularly with a class of galaxies that has proven to be a persistent thorn in the side of the standard dark matter model, the low surface brightness galaxies. These are the faint, ghostly systems where the signal from stars is minuscule and the expected influence of dark matter should be overwhelmingly dominant. According to the lambda-CDM model, predicting the rotation curve of such a galaxy should be incredibly difficult. It depends on the complex and poorly understood history of how the visible galaxy forms within its dark matter halo, a process riddled with variables and feedback mechanisms that can alter the final result. MUND, by contrast, makes a razor-sharp prediction, since it directly links the observed gravity to the observed distribution of stars and gas. All one needs is a map of the visible matter, and the theory predicts the exact rotation curve, the precise speed at which stars and gas should orbit at every distance from the center. Time and again, for galaxy after galaxy, MUND predictions have matched the observed rotations with an accuracy that dark matter models struggle to achieve without careful, after-the-fact tuning. This predictive success is what fuels the passion of researchers like Stacy McGaw, a leading astrophysicist and a prominent proponent of testing alternatives. He has often emphasized that science advances most powerfully when a theory makes a clear, upfront prediction that is later verified by observation, rather than simply retrofitting parameters to explain existing data. For Mund, the rotation curves of low-surface brightness galaxies were a successful prediction made before they were precisely measured, a triumph of foresight that its supporters argue the standard model lacks. Magor and others point to this as a sign that Mund is tapping into a fundamental truth about how gravity operates on galactic scales, a truth that is currently obscured by our insistence on a universe dominated by dark matter. Yet the story is far from one-sided, and the debate between dark matter and modified gravity is one of the most heated and fascinating in all of modern science. Mund, for all its elegance with individual galaxies, faces its own monumental challenges on larger scales. The theory in its basic form has a very difficult time explaining the bullet cluster, a system of two colliding galaxy clusters where the gravitational lensing map shows a clear separation between the mass, which seems to have passed through the collision unscathed, and the visible matter, which was slowed by the drag of intracluster gas. This is interpreted by most cosmologists as direct, visual proof of dark matter, a substance that does not interact with itself or with normal matter except through gravity. Mund proponents have developed more complex relativistic extensions to try and address this, but the solutions often feel less natural than the simple, elegant original premise. Furthermore, the incredible success of the lambda-CDM model in explaining the large-scale structure of the universe, the precise patterns in the cosmic microwave background, and the formation of the cosmic web is a formidable body of evidence that a modified gravity theory must also somehow account for. This leaves us at a profound and thrilling impasse, a true test case that stretches the limits of fundamental physics. Is the universe filled with a mysterious, invisible substance that outweighs everything we can see by a factor of 5 to 1? Or have we, for all our brilliance, slightly miswritten the laws of gravity, and the anomalies we see in galaxies are the first clues leading us toward a deeper, more complete theory, one that might someday reconcile the quantum world with the cosmic? The existence of galaxies whose rotation so perfectly follows Mund predictions is a constant, nagging reminder that our understanding is incomplete. They are the cosmic equivalent of a controlled experiment, testing gravity in the regime where it is weakest and most pure. Whether the final answer lies in dark matter, modified gravity, or some breathtaking synthesis of the two, these anomalous galaxies are the key that will ultimately unlock the next great revolution in our understanding of the cosmos. Yet, even as we stand on the precipice of these revolutionary tools, the ultimate lesson from these cosmic rebels might be one of profound humility. The history of science is littered with moments where we believed we were on the verge of a complete understanding, only to have the universe reveal a deeper, more complex layer of reality. The anomalous galaxies we have explored are not mere footnotes in a textbook. They are glaring headlines in a story we are still learning to read. They remind us that our models, however elegant and mathematically sophisticated, are ultimately approximations, maps of a territory that is far wilder and more wonderful than we ever imagined. The future of cosmology, therefore, is not just about building better telescopes or faster computers, though that is essential. It is about cultivating a mindset of flexibility and wonder, of being willing to follow the evidence wherever it leads, even if it takes us to a universe that looks nothing like the one we thought we knew. This is the grand, unfolding mystery that drives the next generation of discovery, a journey not toward a final answer, but toward a deeper, more meaningful set of questions about the cosmos and our place within it. From ultra-diffuse ghosts to dark matter-deficient enigmas, we've journeyed through galaxies that defy prediction, each one a cosmic rebel refusing to follow the rules we so carefully wrote. These aren't just distant curiosities, they are profound messages from the universe telling us that our current understanding is merely a first draft in an epic story that's still being written. Every time we point our telescopes at the sky, we are humbled and exhilarated by what we find: structures that shouldn't exist, spinning in ways that defy logic, shining with a light that tells a history we don't yet fully comprehend. They challenge the brightest minds in astrophysics not just to find new answers, but to ask entirely new questions, pushing the boundaries of physics, chemistry, and even our philosophy of science itself. This journey through the anomalous and the impossible is far more than a catalogue of cosmic oddities. It is a powerful reminder that the universe is a place of infinite wonder and complexity. It invites every one of us to share in that sense of awe, to look up at the night sky not as a static picture, but as a dynamic, evolving, and deeply mysterious reality. Whether you're a seasoned enthusiast or just beginning to explore the cosmos, these mysteries belong to all of us. They spark our collective imagination and drive the human spirit of discovery forward. So we want to hear from you. Which of these physics-breaking galaxies captured your imagination the most? Was it the serene perfection of Hoag's object, the lonely giant in the void, or the shocking emptiness of a galaxy without its dark matter anchor? Share your thoughts in the comments below. Let's continue this conversation and explore these wonders together. If this journey to the edge of our understanding has sparked your curiosity, make sure to subscribe and hit the notification bell so you don't miss our next deep dive into the wonders of space. There are always more mysteries to unravel, from the enigmatic nature of black holes to the strange physics of the early universe. Your support is what allows us to keep exploring these incredible topics and sharing them with you. Thank you for watching, for wondering, and for being part of this incredible community of cosmic explorers. Never stop questioning, never stop looking up, and always remember that the greatest discoveries often lie just beyond the limits of what we believe is possible. The cosmos always has more